What if I told you that everything we can see, every star, every planet, every galaxy, every particle of dust and gas, makes up just 5% of what actually exists in the universe? The rest, a staggering 95%, is made of something we can't see. It's not that it's hidden behind something or too far away. No, this mysterious majority of the cosmos is simply invisible. It does not emit, absorb, or reflect light. We call it dark matter and dark energy. These are not just exotic scientific terms. They are clues to a deeper reality, one that continues to confound and fascinate physicists and astronomers alike. The universe, as it turns out, is largely unknown. Dark matter alone makes up about 27% of the universe. It's called dark not because it's malevolent or ominous, but because it eludes detection. It doesn't shine or glow. It doesn't block light or cast shadows. It's simply unseen. Yet its presence is undeniable. Scientists know it's there because they can see what it does. Galaxies spin at such high speeds that if only visible matter were present, they would tear themselves apart. And yet, they don't. Something invisible is holding them together. That something is dark matter. It's the glue of the cosmos. We see its fingerprints everywhere. In the way galaxies cluster, in the vast scaffolding of the cosmic web that stretches across space, and in the subtle bending of light, what scientists call gravitational lensing. Imagine looking at a distant galaxy and noticing its image distorted, stretched, or even doubled. That's not a trick of the telescope. That's gravity, bending light around invisible mass. In galaxy clusters, the gravitational pull needed to produce such lensing effects is far more than what the visible matter can account for. The only explanation? A massive unseen component. And so the idea of dark matter was born, not from guesswork, but from gaps in what we could otherwise explain. But what is it made of? That's the question that haunts physicists. Traditional physics, based on everything we know about atoms and particles, can't explain it. This has opened the door to new theories, new particles, and even new dimensions. Scientists have proposed candidates with names like WIMPs, weakly interacting massive particles, and axions. They've built detectors deep underground, shielded from cosmic rays, hoping to catch a rare interaction between a dark matter particle and ordinary matter. They've launched space missions to find clues in the structure and behavior of galaxies. So far, nothing has definitively revealed what dark matter is. And then there's dark energy, an even stranger concept that accounts for nearly 68% of the universe. It's believed to be the driving force behind the accelerated expansion of the universe. While dark matter pulls things together, dark energy pushes them apart. These two unseen forces are locked in a cosmic tug-of-war, shaping the destiny of everything that exists. One of the earliest clues to dark matter came from the rotation curves of galaxies. When astronomers plotted the speed of stars at various distances from the galactic center, they expected to see the velocities drop off at the edges, just like planets in our solar system move slower the farther they are from the sun. But that's not what they saw. Instead, the stars on the outskirts were moving just as fast as those near the center. The only way to make sense of this was to assume that there was much more mass in and around the galaxy than what was visible. This invisible mass, this dark matter, was exerting its gravitational influence. Then came the gravitational lensing studies of galaxy clusters. When light from a distant galaxy travels toward us and passes near a massive object, it bends. The more massive the object, the more pronounced the bending. But the amount of bending observed often exceeds what could be caused by visible matter alone. Again, the conclusion was the same. Something unseen was contributing to the gravitational field. And then there's the cosmic microwave background, the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. Detailed measurements of this radiation reveal tiny fluctuations in temperature that correspond to variations in matter density. These fluctuations, in turn, offer a map of the early universe's structure. But the map doesn't match what we would expect if only visible matter were present. There's simply too much structure, too much clumping. Something else, dark matter, must have helped seed the galaxies and clusters we see today. The story of dark matter is not just a tale of what we can't see. It's a story about how much we have yet to understand. It challenges the boundaries of science. It asks us to imagine what the universe is truly made of, beyond the stars, beyond the galaxies, beyond the reach of light. And in doing so, it invites us to redefine what we think we know. And yet, simulations of cosmic structure formation have added powerful weight to the evidence for dark matter. These models, run on some of the most advanced supercomputers in the world, simulate how galaxies and massive cosmic structures form and evolve over billions of years. When dark matter is included in these simulations, the resulting universe closely mirrors the one we observe today. The way galaxies cluster, the distribution of cosmic voids, and the large-scale web-like architecture of the universe all fall into place if, and only if, dark matter is present. Taken together, this convergence of evidence, from galactic motion and gravitational lensing to the faint echoes of the cosmic microwave background and the digital predictions of supercomputers, paints a picture of a universe deeply shaped by an invisible yet profoundly influential component. This unseen mass appears to outweigh all the ordinary matter in stars, planets, and gas clouds, dramatically altering the structure and destiny of everything we see. Dark matter is one of the most enduring enigmas of modern science. It makes up roughly 27% of the universe's total mass and energy content, yet it does not emit, absorb, or reflect light. We cannot see it, touch it, or photograph it. Its existence is known only through its gravitational pull. And so the hunt continues, not just to confirm its presence, but to reveal its very nature. At the heart of this quest are two leading theoretical candidates: weakly interacting massive particles known as WIMPs and axions. WIMPs are among the most studied and popular possibilities. Predicted by some extensions of the standard model of particle physics, these particles would be heavy, slow-moving, and would only interact via the weak nuclear force and gravity. This subtle behavior would make them nearly invisible to ordinary detection methods, slipping through everyday matter like ghosts. Yet, their mass and gravitational influence could account for the missing mass in the cosmos. If WIMPs are real, they are all around us, passing through Earth and even our bodies by the trillions every second without a trace. To catch one would be a triumph of experimental physics. Around the globe, enormous underground labs have been built with one goal in mind: to observe these particles directly. Deep beneath the Black Hills of South Dakota, the Lux Zeppelin experiment is attempting to do just that. Its tank of ultra-pure liquid xenon is designed to detect the faintest hint of a WIMP colliding with an atom, perhaps a tiny flash of light, perhaps a whisper of ionization. Meanwhile, on the other side of the Atlantic, the CREST experiment in Europe is trying a different strategy. Using crystals chilled to nearly absolute zero, scientists are searching for the smallest burst of heat that might indicate a collision with a dark matter particle. These detectors are shielded by thick layers of rock and advanced engineering, protecting them from the noisy chaos of the surface world. In the quiet underground, they listen patiently for the rarest of signals. And then there are axions, another compelling possibility. Much lighter than WIMPs, these hypothetical particles were originally proposed to solve a puzzle in quantum chromodynamics, the theory that describes the strong nuclear force. If they exist, axions could be drifting through the universe in vast numbers, subtle but pervasive. They would interact so weakly with normal matter that only the most sensitive instruments might ever detect them. If discovered, axions could unlock new chapters in both cosmology and particle physics. There are still other contenders. Sterile neutrinos, more elusive even than the ghostly neutrinos we know, might play a role. Some researchers have suggested primordial black holes, tiny black holes formed in the earliest moments after the Big Bang, as a possible explanation. These remain speculative, but they are part of a broader dynamic field that continues to expand. Dark matter is not merely an academic question. It shapes the way galaxies form and evolve. In the early universe, slight fluctuations in density, tiny wrinkles in the fabric of space, grew under the influence of dark matter's gravity. These became the seeds from which galaxies formed. Without dark matter, these structures would have taken too long to form. There simply wouldn't have been enough time since the Big Bang for the universe to look the way it does today. When we observe galaxies, we see stars orbiting the center far faster than they should, and based on the visible mass alone. Classical physics predicts that stars farther from the center should move more slowly. yet observations show the opposite. The only explanation that fits is the presence of an invisible mass, dark matter, creating a gravitational halo around each galaxy. It is this invisible scaffolding that holds galaxies together, preventing them from flying apart. As galaxies merge and interact, dark matter continues to shape their trajectories. Collisions like the Bullet Cluster provide striking visual evidence. In that system, the visible matter, hot gas, lags behind the bulk of the gravitational mass, which has passed through nearly unimpeded. This displacement can only be explained if most of the mass is made of something invisible. Scientists are using a variety of tools to probe deeper. Telescopes like the Atacama Cosmology Telescope in Chile scan the skies for subtle patterns in the cosmic microwave background, the leftover glow of the Big Bang. These patterns hold clues to how dark matter behaved in the early universe. Satellite missions map gravitational lensing, where massive concentrations of dark matter bend light from distant galaxies, allowing us to see dark matter's distribution across space. All of these approaches are part of a grand scientific enterprise to understand the universe not just as it appears, but as it truly is. Dark matter, it seems, has been silently orchestrating the formation of stars and galaxies since the dawn of time. And yet it remains in the shadows, invisible to our eyes, but not to our curiosity. In laboratories deep beneath the Earth and high above it in space, scientists are designing experiments with precision and patience. Each data point, each detection, or lack thereof, brings us closer to unlocking the secret. The discovery of dark matter's identity would not only revolutionize physics, but would redefine our place in the cosmos. For now, we are guided by gravity's clues and light's distortions, chasing the shadows of something vast, ancient, and unseen. Dark matter is not just a mystery. It is a story still unfolding, a cosmic riddle that may one day reveal the hidden architecture of everything we know. Additionally, international collaborations have given rise to groundbreaking efforts such as the Panda X experiment in China. Here, scientists apply the same guiding principles behind projects like the Lux Zeppelin detector, working tirelessly to capture the faintest whispers of dark matter. These experiments are not confined to a single nation or lab. They are united by a shared ambition to build environments so precise and sensitive that even the rarest interactions between dark matter and ordinary matter might be caught in action. Each setup is an attempt to lift the veil on a cosmic mystery that continues to shape the very structure and destiny of our universe. Dark energy, on the other hand, represents one of the most profound puzzles in modern science. It is not something we can touch, see, or directly measure in the traditional sense, yet it dominates the cosmos, making up nearly 70% of its total energy content. This elusive force is believed to be responsible for the accelerating expansion of the universe, a phenomenon that has upended long-held assumptions about cosmic evolution. Its effects are not subtle. Dark energy exerts a kind of cosmic push, driving galaxies farther apart at an ever-increasing pace. The discovery of this acceleration, made in the closing years of the 20th century through observations of distant supernovae, sent shockwaves through the scientific community. Before this, the prevailing theory suggested that the universe's expansion should be slowing down, gradually pulled back by the gravity of all its mass. Instead, astronomers found the opposite. Galaxies were accelerating away from each other, hinting at the presence of an unknown, invisible energy. That energy became known as dark energy. In contrast, dark matter serves a completely different function in the cosmic narrative. It constitutes roughly 25% of the universe and acts as an invisible framework that holds galaxies and galaxy clusters together. While dark energy pushes, dark matter pulls. Its gravity shapes the formation of galaxies, influences their motion, and provides the unseen glue that binds vast cosmic structures. Though we cannot see dark matter directly, we infer its presence from the way galaxies rotate and interact. Without it, the universe's large-scale architecture simply would not make sense. The fundamental distinction between dark energy and dark matter lies in their opposing effects on the cosmos. Dark energy is expansive, driving everything apart. Dark matter is cohesive, holding things together. One tears at the seams of the universe, the other sews its fabric. These two unseen forces, so vastly different in behavior, together account for 95% of everything that exists. They are the dominant actors in the universe's unfolding drama, even though we still barely understand them. As researchers continue to peel back the layers of these cosmic mysteries, each discovery reshapes our understanding of the universe's past and hints at its future. Will the universe expand forever, its stars fading into darkness in a cold, silent end? Or will other forces, yet unknown, rewrite the rules once again? The journey to uncover the secrets of dark matter and dark energy is more than an academic pursuit. It is a profound quest to comprehend our place in a universe that is still largely unknown. With each experiment, each measurement, and each theoretical breakthrough, we take one step closer to illuminating the cosmic landscape we call home. And yet, dark energy invites even deeper questions about the very essence of space and time. Is it a static, unchanging force woven into the cosmic fabric, or does it fluctuate across the ages, responding to the universe's own evolution? Could it be that what we interpret as dark energy is not a separate force at all, but instead a reflection of our incomplete understanding of gravity? Might the answer lie in the existence of hidden dimensions beyond the familiar three of space and one of time? These are not merely theoretical curiosities. They are questions that may, in time, demand a rewrite of the most fundamental laws of physics. At the heart of this mystery lies a compelling truth. Dark energy dominates the cosmos. Current estimates suggest that it comprises around 70% of the universe's total energy content. Yet its nature remains elusive. It was only in the closing years of the 20th century that the first clues emerged, reshaping cosmology almost overnight. The discovery came through a surprising observation. Distant supernovae, exploding stars that serve as cosmic mileposts, appeared dimmer than anticipated. These type Ia supernovae, used as standard candles due to their consistent brightness, were found to be farther away than expected. That could only mean one thing: the universe's expansion was accelerating. Two independent research teams working in parallel reached the same conclusion. The findings stunned the scientific community. Rather than slowing down under the pull of gravity, the cosmos was speeding up, pushed outward by an unseen force. Further confirmation came from the study of the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. This radiation, still detectable across the sky, carries a delicate imprint of the universe's earliest moments. Space missions like the Wilkinson Microwave Anisotropy Probe, WMAP, meticulously map tiny fluctuations in this ancient light, revealing a cosmos that could not be explained without dark energy. The measurements pointed to a universe that was flat in geometry, but lacking enough matter to account for this flatness, unless dark energy filled in the missing puzzle piece. Additional support arrived from large-scale surveys of galaxies. By charting how galaxies cluster and spread across the cosmos, scientists glean insights into the universe's expansion history. These studies revealed a pattern of structure formation that would be impossible without dark energy's repulsive influence, subtly shaping the cosmic web. Even light itself helped reveal dark energy's fingerprints. Gravitational lensing, where the gravity of massive objects warps and magnifies the light of more distant sources, provided yet another line of evidence. The way light bent around galaxy clusters aligned with models that included dark energy, offering a glimpse into how this mysterious force affects not just motion, but the very shape of space-time. With these diverse lines of evidence converging, a picture began to emerge. Dark energy is not a speculative add-on. It is a central player in the cosmic story, a force that shapes the universe's structure, evolution, and ultimate destiny. To understand dark energy, we must look not only at the present, but also to the very beginning. Shortly after the Big Bang, the universe experienced a mind-bending episode known as cosmic inflation. In a mere fraction of a second, space itself expanded exponentially, smoothing out any initial irregularities and laying the groundwork for the cosmos we see today. Inflation is believed to have been driven by a powerful energy field, one that, like dark energy, exerted negative pressure and repelled gravity. The parallels are striking. Though separated by eons, both inflation and dark energy appear to stem from fields that warp the geometry of the universe. Some theorists even speculate that dark energy could be a lingering echo of inflation, operating on a vastly different timescale and scale of influence. As the universe cooled, matter began to coalesce into stars, galaxies, and clusters. For billions of years, gravity held sway, but eventually dark energy reasserted its presence, tipping the balance and accelerating the cosmic expansion once more. This resurgence became unmistakable in the observations of the late 20th century, and it remains a defining feature of the modern universe. What then is the true nature of dark energy? Several competing hypotheses attempt to answer that question. One possibility is that it is a cosmological constant, a fixed quantity embedded in the equations of general relativity, first proposed by Einstein and later revived. In this model, dark energy is an inherent property of space itself, unchanging and omnipresent. But alternatives abound. Some scientists propose that dark energy is not constant at all, but dynamic, changing with time, and possibly influenced by the evolution of matter and energy in the universe. These models, often grouped under the term quintessence, suggest a field that evolves slowly, potentially revealing new physics as it unfolds. Others explore even more radical ideas. Modified gravity theories challenge the assumption that Einstein's theory remains valid at the largest scales. These models tweak the laws of gravity to explain the observed acceleration without invoking an additional energy component. If correct, they would revolutionize our understanding of how mass and energy interact across the cosmos. Still more speculative are theories involving extra dimensions, an idea rooted in string theory and related frameworks. In this view, what we perceive as dark energy might be the shadow of processes occurring in unseen dimensions, influencing our universe from beyond the veil of perception. Each of these possibilities carries profound implications, not only for cosmology, but for physics as a whole. The mystery of dark energy touches on the deepest questions we can ask. What is the nature of space and time? Why does the universe exist in its current form? And what will be its ultimate fate? As observations improve and new instruments probe the cosmos with unprecedented precision, the answers may come into sharper focus. For now, dark energy remains a cosmic enigma, one that binds together the beginning and the end of time, and challenges us to rethink the very framework of reality. And finally, some physicists are daring to entertain a possibility once relegated to the outer edges of speculation: the multiverse. In this scenario, our universe is not the singular, all-encompassing stage of existence, but rather just one among a vast ensemble of parallel universes. Each of these could possess its own distinct physical laws, constants, and configurations of matter and energy. Within this framework, the mysterious force we call dark energy, often described as the driver of the universe's accelerated expansion, might not be a fundamental component of nature at all. Instead, it could be an emergent feature, a consequence of residing in a universe where these particular laws hold sway. This idea reshapes the very questions we ask about existence. What is the nature of reality if the laws we observe are not universal but circumstantial? What does it mean to live in a cosmos that is just one outcome among countless others? As theoretical models grow more sophisticated and observational tools more precise, these questions are moving from the philosophical to the scientific. The effort to understand dark energy through this lens may one day revolutionize not just our physics, but our conception of everything. When matter or information encounters the event horizon of a black hole, it reaches a frontier of no return. This boundary marks the edge beyond which gravity becomes so overwhelming that not even light can escape. What lies within is hidden from the universe, a realm where familiar physics begins to unravel. It's here, inside the event horizon, that the ordinary structure of space-time gives way to the extraordinary, where the very rules that govern matter, energy, and information cease to operate in any conventional sense. At the core of a black hole lies the singularity, a point of infinite density and zero volume. The gravitational pull here is so intense that the known laws of physics collapse into mathematical singularities, regions where equations yield infinities and predictions become meaningless. Before anything reaches this ultimate core, it is subject to unimaginable forces. Matter falling into a black hole is crushed atom by atom, then further down into subatomic particles. Even these basic building blocks are believed to be deconstructed, transformed into a state that defies our understanding. And then there is the question of information. In quantum mechanics, information about a physical system, its properties, its structure, its identity, is never truly destroyed. Yet when matter carrying this information crosses the event horizon, it appears to vanish. This paradox has haunted physicists for decades. Known as the black hole information paradox, it strikes at the heart of two major theories, general relativity and quantum mechanics. One suggests absolute destruction. The other, absolute conservation. Some theories suggest the information is imprinted on the event horizon itself, like a hologram encoding a history that can never be erased. Others speculate that when black holes eventually evaporate through a process known as Hawking radiation, this information might be released, albeit in a radically altered form. Proposed by Stephen Hawking in the 1970s, Hawking radiation offered a startling revelation. Black holes may not be entirely black. Quantum fluctuations near the event horizon could cause particle-antiparticle pairs to emerge, with one particle falling into the black hole and the other escaping into space. This subtle energy loss means the black hole shrinks. Paradoxically, as it shrinks, it grows hotter, emitting more radiation. If left alone long enough, a black hole could, in theory, evaporate completely. This possibility challenges the long-standing assumption that black holes are eternal, unchanging, and absolute. Despite their invisibility, black holes have left a trail of evidence across the cosmos. Their existence is not just theorized, but observed indirectly through their powerful influence on nearby matter. Stars caught in their gravitational grip swing around invisible centers with velocities and trajectories that betray the presence of something massive and unseen. At the heart of our own Milky Way, a supermassive black hole exerts its influence over a cluster of stars, their orbits spiraling in complex patterns that map out an invisible predator. In some regions of space, we witness matter spiraling into black holes, forming an accretion disk that heats to millions of degrees and emits bursts of X-rays. These X-rays, captured by space observatories, signal not just the presence of black holes, but also their behavior, their feeding patterns, their motion, their dynamic environments. Then, in 2015, came a new form of evidence: gravitational waves. First predicted by Einstein a century earlier, these ripples in spacetime were finally detected when two black holes collided and merged. The waves they produced reverberated across the universe and reached Earth-based detectors, marking a triumph for both theory and technology. These collisions reveal how black holes grow, interact, and shape the large-scale structure of the universe. Together, these observations build a portrait of black holes as complex, dynamic, and central to the evolution of the cosmos. Once thought to be mere endpoints of stellar collapse, they are now seen as engines of transformation, sculptors of galaxies, and testing grounds for our deepest physical theories. The study of black holes stretches the limits of what we know and what we dare to imagine. They connect the very small with the very large, quantum mechanics with general relativity, particles with space-time itself. In exploring them, we are not just probing strange corners of the universe. We are confronting the limits of human knowledge, and perhaps inching closer to a unified understanding of nature's most elusive truths. Moreover, the discovery of Hawking radiation opens a vast realm of questions regarding the nature of information in our universe, particularly when it comes to the fate of matter consumed by a black hole. What happens to the information embedded in that matter as a black hole evaporates? This question has ignited intense debates among physicists, leading to the exploration of novel principles such as the holographic principle. The holographic principle suggests that all the information contained within a three-dimensional space could, in theory, be encoded on the boundary of that space, offering a potential solution to the so-called information paradox. Resolving this paradox is critical for advancing our understanding of both quantum mechanics and general relativity, two pillars of modern physics that have long remained separate in their foundational approaches. Hawking radiation itself has revolutionized our comprehension of black holes and their role within the cosmos, bridging the oddities of quantum mechanics with the grandeur of cosmology. It challenges the very perception of what black holes are and how they interact with the universe around them. As we continue to delve deeper into the mysteries surrounding these enigmatic cosmic structures, the implications of Hawking's insights remind us of the profound interconnectedness of all elements in the universe, whether they exist at the level of quantum particles or across the vast, sweeping scale of galaxies. Supermassive black holes stand as some of the most enigmatic and awe-inspiring structures in the cosmos, often positioned at the centers of galaxies, including our own Milky Way. The process of their formation likely begins with the birth of smaller black holes, which arise from the collapse of massive stars. Over time, these relatively small black holes can accumulate additional mass, growing larger through a variety of mechanisms. They might merge with other black holes or draw in vast amounts of gas and dust from their surroundings in a process known as accretion. As this material spirals inward, it heats up to incredible temperatures, resulting in the growth of the black hole. This process can continue until the black hole reaches truly massive scales, with some supermassive black holes exceeding billions of times the mass of our Sun. The emergence of supermassive black holes is not a random occurrence. Rather, their formation plays a critical role in shaping the galaxies in which they reside. As they grow, they exert an immense gravitational influence on the stars, gas, and other material in their vicinity, helping to organize the structure of the galaxy itself. This gravitational pull has far-reaching consequences, influencing the dynamics of the galaxy's material and even driving the formation of new stars. In fact, these black holes can regulate star formation within their host galaxies by emitting powerful jets and winds that sweep away gas and dust from the inner regions of the galaxy. By doing so, they limit the available material for new star formation, thus playing a role in the life cycle of galaxies. Moreover, a fascinating connection exists between the size of supermassive black holes and the structure of the galaxies they inhabit. Research has shown that the mass of a supermassive black hole is closely linked to the mass of the galaxy's bulge, suggesting a mutual relationship between the black hole and its host galaxy. As the black hole evolves, it influences the growth and characteristics of its galaxy, leaving a significant imprint on the galaxy's structure and overall dynamics. This relationship hints at a process of coevolution, where both the black hole and the galaxy shape one another over time. The influence of supermassive black holes extends far beyond the confines of individual galaxies. These extraordinary entities are thought to have played a pivotal role in the early universe, helping to seed the formation of the very first galaxies. By understanding the formation and evolution of supermassive black holes, astronomers gain valuable insights into the broader cosmic tapestry, the intricate dance of dark matter, gravity, and luminous stars, all of which influence one another, becomes evident, underscoring the deep interconnectedness of the universe. Primordial black holes, another type of black hole, add to the mystery of the universe. These hypothetical objects are believed to have formed in the very early stages of the universe, shortly after the Big Bang. Their origin is fundamentally different from the black holes we typically study, which generally arise from the collapse of massive stars. Instead, primordial black holes may have formed from high-density fluctuations in the very fabric of space-time. These early black holes could have a wide range of sizes, from tiny objects with masses smaller than asteroids to larger ones that may rival or exceed the mass of massive stars. Despite their intriguing nature, many questions remain about primordial black holes. One of the key unresolved issues is their mass distribution. Scientists are eager to understand how many primordial black holes exist and what their mass range might be. While some theories suggest a wide array of sizes, ranging from microscopic black holes to those with several times the mass of our Sun, definitive evidence remains elusive. This lack of conclusive data prevents scientists from fully understanding the population of primordial black holes and their role in the universe. A crucial question revolves around the potential connection between primordial black holes and dark matter, the mysterious substance that constitutes a significant portion of the universe's mass. Could primordial black holes be a significant component of dark matter? This possibility is actively being investigated, but the connection remains speculative. If primordial black holes do indeed account for some fraction of dark matter, it would open up new avenues of research into how these objects interact with other forms of matter and energy in the cosmos. Detecting primordial black holes presents a significant challenge. While astronomers have observed numerous black holes through various means, primordial black holes could be far more elusive, leaving only faint signals that are difficult to detect. Some potential detection methods include gravitational lensing, the analysis of cosmic microwave background radiation, or even the possible detection of Hawking radiation itself, a theoretical type of radiation predicted by physicist Stephen Hawking. Until conclusive evidence can be gathered, primordial black holes remain one of the most fascinating and elusive mysteries in the field of cosmology. The moment before the Big Bang, often referred to as the beginning of time, is one of the most profound and enduring enigmas in cosmology. For decades, scientists have grappled with the question of what could have existed prior to this cataclysmic event. While numerous theories have emerged, each offering its own perspective on the origins of our universe, all of them push the boundaries of our current understanding. One compelling theory suggests that time and space themselves were created during the Big Bang. According to this perspective, asking what happened before the Big Bang may be a fundamentally flawed question. If time itself began with the Big Bang, then there was no before in the traditional sense of the word. This idea challenges our very understanding of time and raises questions that are both scientific and philosophical in nature, blurring the line between the two realms. Another widely accepted theory is that of cosmic inflation. This concept proposes that the universe underwent a rapid and dramatic expansion shortly after the Big Bang, accelerating at an unimaginable rate. Some scientists suggest that this inflationary period could have been preceded by an entirely different era or even a different universe, potentially leading to a cycle of Big Bangs and collapses. Under this scenario, our universe could be one of many bubbles in an ever-expanding cosmic foam, a concept known as the multiverse theory. This idea suggests that the universe we inhabit might not be the only one, and the Big Bang could have been merely the birth of one universe in a vast, infinite multiverse. The possibility of a multiverse fundamentally challenges the way we think about the nature of existence, offering a radically different perspective on the origin and evolution of the cosmos. Whether or not these theories will ultimately prove correct remains to be seen, but they exemplify the incredible complexity and mystery surrounding the origins of our universe, a mystery that continues to captivate the minds of scientists and philosophers alike. Quantum fluctuations are one of the most intriguing concepts in modern cosmology. These tiny, random shifts at the subatomic level hint at the possibility that our universe could have emerged from an initial chaotic state of energy. Imagine, if you will, an ocean of energy constantly fluctuating with brief moments of instability. In this view, these fluctuations could have sparked the creation of a mini-universe, tiny and fleeting at first, before it rapidly expanded, giving rise to the Big Bang. It's a hypothesis that suggests the universe might have been born out of a kind of cosmic randomness, a thrilling idea that keeps scientists questioning the very nature of existence. However, the beauty of these theories lies not just in their audacity, but in the questions they raise. How did this chaotic energy manifest into the ordered universe we see today? What was the driving force behind the expansion? Each theory presents an array of possibilities, opening new doors of exploration. This is the essence of scientific discovery, where the more we uncover, the more we realize just how much is still out there, waiting to be understood. Even our origins, the very foundation of everything, remain shrouded in mystery and speculation, an exhilarating puzzle that continues to unfold. To piece together the conditions of the early universe, just moments after the Big Bang, scientists rely on a blend of theoretical models, astronomical observations, and cutting-edge experimental physics. One of the most crucial methods in this endeavor is the study of cosmic microwave background radiation, often abbreviated as CMB. This faint afterglow, a remnant from a time when the universe was a dense, hot soup of particles, was released around 380,000 years after the Big Bang. The CMB acts as a snapshot from that early era, providing a direct window into the universe's infancy. By examining the subtle temperature fluctuations in the CMB, scientists can infer vital details about the state of the universe at that time. These minute variations in temperature are like ripples in a pond, revealing the density and distribution of matter during the universe's formative years. In turn, this data offers crucial insights into how the universe evolved, helping scientists refine their understanding of cosmic events that shaped the world we now observe. Another powerful tool in understanding the early universe is the use of particle accelerators, such as the Large Hadron Collider, LHC. These sophisticated machines recreate conditions that mimic those just after the Big Bang, allowing physicists to study particles at the smallest, most fundamental level. By smashing protons together at nearly the speed of light, they can observe the forces and particles that were prevalent in the nascent universe. These experimental findings shed light on the building blocks of matter and the fundamental forces that govern the cosmos. It's like peering back through a cosmic microscope, gaining insights into the very fabric of the universe. Additionally, computer simulations play an indispensable role in modeling the early universe's evolution. These simulations, based on the laws of physics, take into account factors like expansion, cooling, and the formation of structures like galaxies. By comparing the outcomes of these models with actual observations, researchers can refine their theories and narrow down the many possibilities for how the cosmos took shape. Finally, observations of distant galaxies provide another fascinating piece of the puzzle. The light from these faraway galaxies has traveled across billions of years before reaching us, offering a glimpse into how they formed and evolved. Through these cosmic observations, astronomers can trace the history of galaxy formation and understand how matter has been distributed throughout the universe. This combination of diverse research methods, from studying the CMB and particle collisions to analyzing distant galaxies, is gradually unveiling the mysteries of the universe's earliest moments. The cosmic microwave background radiation, often regarded as the universe's first light, is a relic from the Big Bang. This faint afterglow bathing the universe is a remnant from when the cosmos was a hot, dense particle soup. Approximately 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine, forming neutral hydrogen atoms. This allowed light to travel freely for the first time, marking a pivotal moment in the universe's evolution, often referred to as the decoupling era. The discovery of CMB in the 1960s provided compelling evidence for the Big Bang theory. Upon analyzing this uniform radiation, scientists noted that while it appeared mostly uniform across the sky, it contained tiny fluctuations, minuscule variations in temperature and density. These fluctuations are essential, as they serve as the cosmic blueprint for the formation of galaxies and large-scale structures that we observe today. The CMB, therefore, not only provides a snapshot of the universe's infancy, but also offers critical insights into the processes that have shaped the cosmos over billions of years. Through precise measurements of the CMB, scientists have been able to determine key properties of the universe, including its age, composition, and rate of expansion. For instance, the CMB has revealed that the universe is approximately 13.8 billion years old. It also shows that dark energy and dark matter make up most of the universe, while ordinary matter accounts for only a small fraction. These findings have revolutionized our understanding of the cosmos and raised profound questions about the nature of dark energy, which appears to be driving the accelerated expansion of the universe. The CMB is, in essence, a cosmic time capsule. It allows us to peer into the distant past, providing critical clues about the universe's birth and evolution. As technology continues to advance, scientists are able to probe deeper into the CMB, unveiling even more insights and refining our understanding of the universe's earliest moments. Each discovery takes us one step closer to unlocking the secrets of the cosmos and understanding our place within it. While the Big Bang theory remains the dominant explanation for the origin of the universe, alternative models have recently gained traction among researchers. One such theory is the steady-state model, which proposes that the universe, despite its expansion, maintains a constant average density. In this model, new matter is continuously created to fill the void left by galaxies as they move apart, suggesting a universe that is eternal and unchanging. Another captivating idea is the cyclic model. According to this theory, the universe undergoes an infinite series of expansions and contractions. Each cycle begins with a big bang, followed by a big crunch, in which the universe collapses back on itself. After this collapse, another explosion occurs, leading to a new expansion phase. This model raises profound questions about the nature of time and reality, suggesting that the universe may have experienced, perhaps even continues to experience, an endless cycle of birth, death, and rebirth. Both of these alternative models invite us to rethink our understanding of the cosmos. What if the universe is not a singular event, but part of an eternal cycle? What if time itself is not linear, but cyclical, with an infinite number of cosmic beginnings and endings? These questions, raised by the steady-state and cyclic models, challenge our most fundamental assumptions about the universe, and may one day offer new answers that reshape our view of the cosmos. Each of these theories, whether mainstream or alternative, opens a window into the vast unknown, where mystery and discovery intersect. And in that space between what we know and what we have yet to understand, the journey of scientific exploration continues. Pushing the boundaries of our knowledge and forever transforming our conception of the universe. Physicists are increasingly turning their attention to the idea of a multiverse, a concept that could forever change the way we understand our existence. Imagine, if you will, that our universe, the vast cosmos we've spent centuries exploring, is merely one among many. Each of these universes could have its own unique set of physical laws and constants, and some theories even propose that separate bubbles of spacetime could emerge, each with a distinct cosmic history. This bold hypothesis challenges everything we thought we knew about the universe. It raises profound questions about the very nature of existence and our place in this vast cosmic sea. While theories of the multiverse are not yet widely accepted in mainstream science, they have sparked vibrant debates within the scientific community. These alternative models of the universe encourage a rethinking of the Big Bang theory, which has long been the cornerstone of cosmology. The multiverse theory serves as a reminder of the dynamic and evolving nature of the field, prompting questions that are as exciting as they are enigmatic. In this ever-changing landscape, every new theory unravels more mysteries, ensuring that our quest to understand the cosmos remains as alive and compelling as ever. As we peer deeper into the vastness of space, we are confronted with the mysterious origins of the universe, particularly the earliest moments following the Big Bang. Theories like cosmic inflation have shaped much of our current understanding. According to this theory, the universe experienced an incredibly rapid expansion in its infancy, a moment of inflation that set the stage for the creation of the vast structures we observe today. However, there's much we don't yet know about this primordial period. Future discoveries may radically alter our understanding of how galaxies, stars, and planets formed over billions of years. For instance, our models of the universe's evolution could be completely transformed by new insights into dark matter and dark energy, two of the most mysterious forces in cosmology. Dark matter, which remains invisible yet makes up around 25% of the universe, plays a crucial role in shaping the structure of galaxies. A deeper understanding of its properties could completely rewrite our theories about how stars and galaxies came into being. Similarly, dark energy, the force responsible for the universe's accelerating expansion, might alter our views on the universe's ultimate fate. Will the universe continue to expand forever, or will it eventually collapse? What's more, technological advancements in the coming years may allow us to peer further back in time than ever before. More powerful telescopes, along with cutting-edge gravitational wave detectors, may unlock new insights into the early moments of the universe. We could, for example, capture signals from the cosmic microwave background radiation, the faint glow left over from the Big Bang itself. These early signals might offer us a clearer picture of the universe's infancy and allow us to test our current models of cosmic evolution. With each new discovery, we may encounter new puzzles that force us to re-examine old ones, ultimately leading to a more complete understanding of the universe's origins. These discoveries have profound implications, not just for the field of cosmology, but for our broader philosophical understanding of existence. They invite us to contemplate questions about why the universe is structured as it is today and what that means for our place within it. The universe, with all its mysteries, continues to surprise us, compelling us to look deeper and think bigger as we search for the answers to some of the most fundamental questions about our reality. One of the most mind-bending areas of research in modern physics is quantum mechanics. This branch of science challenges our traditional, everyday understanding of how the universe works. At its core, quantum mechanics reveals a world where particles behave in ways that seem almost impossible. At the smallest scales of energy and matter, particles don't behave according to the predictable laws of classical physics. Instead, they exist in a state of probability, meaning we can't know their exact state until we observe them. This introduces a level of uncertainty and complexity that seems to defy the intuitive logic we rely on in our daily lives. Quantum mechanics has led to ideas that are nothing short of extraordinary. For instance, particles can exist in multiple places at once, a phenomenon known as superposition. Imagine an electron that could be in more than one place or have more than one energy state at the same time, but only when it is not being observed. Once we measure it, it collapses into a single state. This idea turns our conventional understanding on its head, where we expect particles to occupy only one state at a time. Another striking example of quantum behavior is entanglement, a phenomenon so strange that even Albert Einstein called it spooky action at a distance. When two particles become entangled, their states are linked in such a way that the state of one will instantaneously affect the state of the other, regardless of the distance separating them. This mysterious connection between particles forces us to reconsider what we think we know about information and connection in the universe. How can information travel so quickly, faster than the speed of light, without violating the laws of physics? Quantum mechanics forces us to rethink the very nature of reality itself. Instead of being a fixed, deterministic world, the quantum realm suggests that the act of observation plays a crucial role in shaping the outcome of events. This raises an intriguing question. Are we simply passive observers of the universe, or do we play an active role in bringing certain realities into existence? This philosophical conundrum has profound implications for both science and metaphysics, urging us to reconsider our role in the cosmos. As we delve further into the quantum world, we encounter more questions and fewer definitive answers. The behavior of particles at this scale is so complex and counterintuitive that it challenges everything we thought we knew about reality. Yet these puzzles are what make quantum mechanics so fascinating, offering a deeper understanding of how our universe operates at its most fundamental level. Quantum entanglement, one of the most fascinating aspects of quantum mechanics, also carries profound implications for our understanding of the cosmos. In essence, it describes the phenomenon in which two or more particles become so deeply connected that the state of one particle will instantly influence the state of the other, regardless of the distance between them. This defies our everyday experiences of separateness in space and time. On a microscopic scale, entanglement is central to many quantum processes, such as particle decay and the interactions that govern the building blocks of matter. These entangled particles share information about their states in such a way that their behaviors are inseparable. This interconnectedness is vital for understanding the nature of high-energy environments like those inside stars or in the chaotic conditions of the universe shortly after the Big Bang. Beyond the subatomic level, entanglement may also have cosmological significance, especially when it comes to the formation and evolution of galaxies. Some theorists suggest that quantum effects may have shaped the distribution of matter in the early universe, ultimately influencing the formation of galaxies. This idea invites us to consider how deeply entangled the quantum world is with the cosmic order, suggesting that what happens at the smallest scales has lasting consequences on the largest scales of the universe. As we continue to explore these strange and enigmatic realms of physics, we are constantly reminded that the universe is far more interconnected and complex than we can possibly imagine. Each discovery peels back another layer of the cosmos, revealing new dimensions and untold mysteries waiting to be unraveled. As we venture further into the realms of cutting-edge technologies like quantum computing and quantum communication, the concept of quantum entanglement is becoming ever more significant. These technologies rely on the extraordinary properties of entangled particles, enabling highly secure information transfer that is virtually impervious to tampering. As we begin to harness the power of entanglement, we may not only unlock transformative, practical applications here on Earth, but also uncover deeper insights into the nature of the cosmos itself. The more we delve into the intricacies of quantum entanglement, the more we come to realize that it is embedded at the very heart of reality itself, challenging our understanding of space, time, and the interconnectedness of all things. This realization raises fundamental questions. If the fabric of reality is so deeply influenced by quantum entanglement, what does it imply for our own place in the vast universe? How does our understanding of reality shift when we consider that the universe might be fundamentally interconnected at a level we cannot yet fully grasp? One of the most profound challenges in contemporary physics is reconciling two of the most successful theories ever developed: quantum mechanics and general relativity. Quantum mechanics, which governs the microscopic world of atoms and subatomic particles, has revolutionized our understanding of the very building blocks of nature. On the other hand, general relativity, which explains gravity and the large-scale structure of the universe, has provided unparalleled insights into the behavior of stars, planets, and galaxies. Despite their individual successes, these two theories are fundamentally incompatible when applied to certain extreme conditions, such as black holes or the early moments of the Big Bang. In these high-energy environments, the laws of quantum mechanics and general relativity seem to contradict one another. The question of how to bridge this gap has become a central focus in modern theoretical physics. Several promising ideas are emerging, each seeking to unify these two seemingly irreconcilable frameworks. One such theory is quantum gravity, a field of study aiming to create a unified description of the quantum nature of space, time, and gravity. Among the most prominent approaches are string theory and loop quantum gravity. String theory suggests that the fundamental particles of nature are not point-like, but instead tiny, vibrating strings. This theory proposes not only a way to combine the quantum and gravitational realms, but also suggests the existence of additional spatial dimensions beyond the familiar three that govern our everyday experiences. Meanwhile, another exciting avenue of research centers on the very nature of spacetime itself. According to general relativity, spacetime is a smooth, continuous fabric that bends in response to the presence of mass and energy. Yet quantum mechanics introduces the idea that at the smallest scales, spacetime might be discrete or even exhibit a foamy structure, with fluctuations that could lead to unpredictable changes. This creates a picture of the universe where the smooth fabric of spacetime is at once both malleable and fundamentally uncertain at the quantum level. These ideas, when combined, suggest that our current understanding of the universe may need a complete overhaul. What if the universe operates on a set of rules that we have yet to discover, rules that are governed by both the incredibly small quantum phenomena and the vast forces of gravity? The exploration of these ideas could completely reshape our view of the cosmos, revealing deeper truths about the forces that govern reality. Even as scientists grapple with these complex questions, one of the most exciting aspects of modern physics is the realization that quantum phenomena are not just theoretical concepts. They are directly connected to the very evolution of the universe. Quantum fluctuations, the tiny, inherent variations in energy fields at the subatomic level, played a pivotal role in the early stages of the universe, influencing its growth and structure in profound ways. After the Big Bang, the universe was filled with these fluctuations, creating a dynamic and ever-changing energy field. Over time, these fluctuations gave rise to variations in the density of matter, some regions becoming slightly more dense than others. As gravity began to act on these denser pockets, it pulled the matter together, ultimately leading to the formation of the first gas clouds, stars, and over billions of years, galaxies. Without these quantum fluctuations, the universe might have remained a more uniform, less structured expanse, lacking the rich tapestry of galaxies and cosmic objects we observe today. In this way, quantum fluctuations acted as the seeds for the formation of the universe's large-scale structures. These tiny, Seemingly inconsequential variations in energy served as the foundation for the complex web of galaxies that would eventually form. They serve as a crucial link between the strange, probabilistic world of quantum mechanics and the majestic, ordered structure of the cosmos. Furthermore, the study of these fluctuations opens the door to new possibilities in our understanding of dark matter, an enigmatic substance that accounts for about 27% of the universe's total mass. Although we cannot directly detect dark matter, we know that it exerts a gravitational pull that influences the behavior of galaxies and other large-scale cosmic structures. Some researchers believe that quantum fluctuations, particularly those occurring during the universe's early inflationary period, may hold the key to understanding how dark matter interacts with the rest of the universe. The idea is that during the inflationary phase, the rapid expansion of the universe could have created density variations that eventually seeded the formation of galaxies, clusters, and other cosmic structures, all of which were influenced by dark matter. By studying these fluctuations, scientists hope to uncover more about how dark matter behaves and its role in shaping the universe's evolution. The implications of these findings are profound. Understanding quantum fluctuations might not only illuminate the origins of cosmic structures, but also provide vital clues about the fundamental forces that govern the universe, forces that remain largely mysterious. In this way, the study of quantum fluctuations is offering a new way to think about the cosmos, as a unified whole where the infinitesimally small and the magnificently large are deeply interconnected. As scientists continue their search for answers, one thing is certain: the universe is far more intricate and complex than we ever imagined. The quest to understand quantum mechanics, general relativity, and the very nature of reality is only just beginning. Each discovery leads to new questions, and every breakthrough brings us closer to understanding the fundamental truths of our existence in this vast, mysterious cosmos. Researchers are increasingly exploring the complex implications of quantum entanglement and its connection to the enigmatic nature of dark matter. As our understanding of these phenomena deepens, scientists are considering whether dark matter could possess quantum properties that might alter our perception of gravitational interactions on a cosmic scale. If dark matter is indeed governed by quantum principles, it could fundamentally challenge and reshape how we view the universe, revealing hidden dimensions of reality that remain elusive to us. The investigation into dark matter's potential quantum characteristics is more than a simple academic curiosity. It holds the promise of opening new avenues for exploring the universe's most mysterious components. This fascinating field of research, which blends quantum mechanics with cosmology, could lead us to insights that not only transform our understanding of dark matter, but also change how we think about the very fabric of space and time. As experiments continue and observational technology advances, the relationship between quantum mechanics and dark matter could reveal secrets that have remained hidden since the dawn of the universe. At the heart of many contemporary cosmological theories is the idea of the multiverse, the notion that our universe may be just one of an infinite number of universes that exist simultaneously. This profound theory suggests that each universe within the multiverse could operate according to its own distinct set of physical laws, constants, and properties. In this vast cosmic landscape, some universes might be hospitable to life, while others may be entirely incapable of supporting the conditions we deem necessary for existence. Imagine the universe as a vast cosmic sea, where each bubble represents an independent universe, with environments ranging from those perfectly suited for life to those that are alien to our very concept of existence. The origins of the multiverse concept can be traced back to quantum mechanics, particularly through the lens of the many worlds interpretation. According to this perspective, every quantum event, no matter how small or seemingly insignificant, splits into multiple possibilities, each one giving birth to a new universe. This branching of realities means that the history of our own universe is just one of countless possible outcomes, a single thread in the intricate weave of infinite realities. The idea that every quantum decision branches into new realities challenges our conventional view of time and existence, suggesting that what we perceive as linear history might actually be a vast network of interconnected potential outcomes. Beyond the realm of quantum mechanics, the multiverse theory has found support in the fields of cosmology and string theory. These theories suggest that the fundamental structure of reality may allow for the existence of multiple parallel universes. According to current cosmological models, the phenomenon known as cosmic inflation, the rapid expansion of the universe shortly after the Big Bang, could naturally give rise to separate bubbles of space-time. Each of these bubbles could form its own distinct universe, governed by its own set of physical laws. While the evidence for such multiverses remains speculative, the idea is bolstered by certain features of our universe, such as the observed fine-tuning of physical constants. Some researchers argue that these constants are so perfectly calibrated for life as we know it, that it seems likely our universe is just one of many, each with a different set of constants that may or may not allow for life. As we continue to look deeper into the cosmos, the implications of the multiverse theory challenge not only our understanding of the physical universe, but also the very nature of existence itself. If the multiverse exists, what does that mean for our place in the grand scheme of things? How do we define reality when the scope of possible realities stretches far beyond what we can currently observe or imagine? The theory invites us to reconsider the limits of observational science, suggesting that the universe we can see and measure might only be a small fraction of a far larger and more intricate reality. One of the most profound implications of the multiverse theory is the way it could redefine our understanding of the fundamental laws of physics. If each universe within the multiverse has its own unique set of physical laws and constants, the nature of those laws could vary drastically from one universe to another. In one universe, gravity might be weaker than in ours, while in another, the rules governing atomic interactions could be completely different. Such variations would fundamentally challenge the notion of universal truths. The constants we observe might not be as universal as we think. Instead, they could be a rare and localized set of conditions, the result of a specific set of circumstances that led to the formation of our universe. For instance, certain constants in our universe, such as the speed of light or the charge of an electron, appear to be finely tuned to allow for life. If the values of these constants were even slightly different, life as we know it might not be possible. However, in other universes within the multiverse, these same constants might have entirely different values, leading to environments that are either inhospitable to life or completely alien in nature. This opens up intriguing questions about the origin of our universe. If the creation of the multiverse is driven by mechanisms we are just beginning to understand, such as quantum fluctuations or cosmic events, could the physical laws of our universe be the result of a specific set of initial conditions unique to our reality? The idea that our universe arose from a process capable of producing other universes radically alters how we think about the nature of reality. It suggests that our understanding of the laws of physics could offer clues to the workings of the multiverse as a whole. This view implies that the mechanisms responsible for the formation of these universes might be governed by principles we are only beginning to comprehend. The pursuit of these ideas represents a bold frontier in modern science, but as researchers attempt to understand not only the origins of our own universe, but also the broader implications of a reality that could be far more expansive than we ever imagined. If the multiverse theory is correct and infinite universes exist, the potential implications for physics are enormous. Our fundamental laws may not be universal truths, but rather localized phenomena that are part of a much larger and more intricate picture of reality. This realization would force us to rethink our place in the cosmos and challenge the very nature of existence itself. The infinite variety of universes within the multiverse sparks a sense of awe and wonder, underscoring just how much we have yet to discover about the universe, and perhaps about ourselves. The multiverse theory also forces us to confront new questions about probability and the nature of existence. If there are indeed infinite universes, then what we consider possible in our own reality could be vastly expanded. In this context, what seems improbable or even impossible in one universe might be commonplace in another. Imagine the concept of fate or destiny within a single universe, where certain events appear predetermined or highly unlikely. In a multiverse, however, every conceivable outcome could unfold in some corner of reality, turning the improbable into a near certainty somewhere in the vast expanse of existence. This challenges our notions of free will, choice, and the ultimate meaning of events. In this new framework, the multiverse suggests that there may be no single definitive timeline for existence. Instead, every possible scenario could play out in some form, rewriting our understanding of time, fate, and the significance of our choices. It is a vision of reality that is far more expansive and intricate than we have ever dared to imagine, reshaping our conception of what it means to exist in the cosmos. Furthermore, the multiverse theory encourages a radical shift in how we perceive existence itself. If every universe within this vast cosmos operates under its own distinct set of characteristics, could the fundamental laws that govern these universes be vastly different from one another? This opens up a world of provocative questions. Are the laws and constants that define our universe uniquely special, or are they simply one set of possibilities in a far larger cosmic landscape? Such contemplations carry us beyond the realm of physics and into the domain of philosophy, challenging our understanding of consciousness, identity, and the very essence of reality. They invite us to question the fundamental nature of what it means to be. At its core, the multiverse theory recontextualizes our understanding of chance and the role we play in the grand narrative of existence. It suggests that the reality we know is only one thread in a much broader, more intricate tapestry, expanding the horizons of what's possible. Each universe, according to this theory, could offer different answers to the same fundamental questions, urging us to rethink our assumptions about probability, destiny, and the underlying structure of reality itself. By framing the multiverse as a collection of infinite universes, it transforms our perception of existence, suggesting that the fabric of reality is far more diverse and interconnected than we could have ever dreamed. The very notion of the multiverse posits that our universe may be just one of an innumerable number of universes, each with its own unique physical laws and constants. This captivating idea is not a mere product of science fiction. Rather, it arises from the latest theories in cosmology, which are deeply concerned with explaining why our universe seems so exquisitely tuned for life. Various multiverse models offer different explanations for how these alternate universes might arise, each rooted in complex physical mechanisms. One of the most widely discussed frameworks for the multiverse comes from the theory of cosmic inflation. According to this model, in the universe's earliest moments, it underwent an incredibly rapid and expansive phase, blowing up exponentially in a fraction of a second. During this intense period, tiny quantum fluctuations emerged, microscopic ripples in the fabric of space and time that would eventually give rise to an array of bubble universes. These bubbles, each isolated from the others, could have formed with different physical constants depending on the underlying dynamics of inflation itself. As a result, some bubbles may have birthed universes where the strong nuclear force is dominant, while others may have produced worlds governed by a weaker nuclear force or even different laws of nature altogether. This presents a striking realization. Our universe, which fosters the complexity and beauty of life as we know it, could be just one possibility out of countless others. String theory introduces another intriguing avenue for exploring the multiverse. It suggests that our universe, as we experience it, may be shaped by additional spatial dimensions beyond the familiar three. These dimensions, though imperceptible to our senses, might influence the constants that define our physical reality. The way these extra dimensions fold and compact themselves could lead to a vast range of variations in the nature of the forces and particles that exist within different universes. If the dimensions of space could be arranged differently, they might give birth to entirely new laws of physics, meaning that what we perceive as fundamental constants in our universe could simply be one configuration among many awaiting discovery. The many worlds interpretation of quantum mechanics presents yet another possibility. In this interpretation, the universe continuously branches into multiple realities, each representing a different outcome of every quantum event. This means that for every decision, every random event, or every potential outcome, a new universe is born, each with its own set of physical constants. In this view, the universe we inhabit is merely one of an uncountable number of parallel realities, each one an expression of a different version of reality, where everything that could happen does happen in some universe. Together, these theories paint a picture of a multiverse teeming with diversity, a cosmic landscape far richer and more complex than we could have ever imagined. The differences in physical constants across these universes are not just peculiarities of our own reality, they may be inherent features of a much larger and more varied cosmos. As we begin to explore these possibilities, we gain not only deeper insight into the fundamental nature of our own universe, but also a new sense of wonder and excitement at the infinite possibilities that lie beyond our immediate perception. Yet, the multiverse theory presents significant challenges for those who seek to validate it. Unlike stars, planets, and galaxies, other universes are beyond the reach of direct observation. We cannot detect them with conventional instruments, and this makes empirical testing a near impossible task. Even if we could conceive of a method to detect other universes, the nature of the multiverse may make it impossible to interact with them. Each universe, as defined by the various multiverse models, operates independently, and the laws governing them may prevent any exchange of information or matter between them. This means that much of the theorizing about other universes remains speculative, valuable in stimulating intellectual curiosity, but difficult to prove or disprove through conventional scientific methods. This limitation forces scientists to rethink their approach. In the absence of direct evidence, they must search for indirect signs of the existence of other universes. One promising avenue lies in the study of cosmic background radiation, the faint afterglow of the Big Bang. Variations in this radiation could potentially offer clues about interactions between universes, or the influence of a neighboring universe on our own. Similarly, scientists are investigating the rate of cosmic expansion, looking for anomalies that could suggest that our universe is not an isolated entity, but part of a much larger multiversal system. The mathematical framework required to describe these theories also presents significant hurdles. Many multiverse models draw on the advanced theories of physics, such as string theory or the theory of cosmic inflation. These models are intellectually compelling, yet they often require assumptions that are impossible to test. The abstract nature of the mathematics involved can lead to fascinating speculations, but these ideas may not be directly tied to observable predictions, making it difficult to definitively confirm or refute the existence of other universes. Despite these challenges, the pursuit of understanding the multiverse remains one of the most exciting frontiers in modern science. Researchers continue to explore new methods of inquiry, searching for subtle irregularities or unexplained phenomena in the cosmos that might hint at the existence of other realms. These cosmic investigations are not only important for deepening our understanding of the laws that govern our own universe, but also for keeping alive the spirit of scientific discovery that has always driven humanity to look beyond the familiar and into the unknown. Gravity, the force that binds the universe together, plays a pivotal role in shaping the structure of the cosmos, from the smallest clusters of stars to the largest galaxies. It is the invisible hand that organizes the matter of the universe, orchestrating the formation of celestial bodies and guiding their movements across the vast emptiness of space. In the aftermath of the Big Bang, the universe was an incredibly hot, dense soup of particles. As it expanded and cooled, fluctuations in density began to emerge, sowing the seeds for the vast structures that would later form galaxies, star systems, and even larger cosmic filaments. The pull of gravity caused these tiny fluctuations to accumulate into clumps of matter, which then attracted more particles, eventually coalescing into stars and galaxies. Over time, these galaxies interacted with each other, forming clusters and superclusters of galaxies that stretched across the cosmos. This cosmic network of galaxies, known as the cosmic web, is one of the most awe-inspiring features of the universe. Within this web, vast regions filled with galaxies are surrounded by enormous voids, vast expanses of space where matter is scarce. Gravity's influence does not stop at the formation of galaxies. It also dictates their evolution over time. As galaxies merge and collide, their gravitational interactions reshape their structures and give rise to new cosmic formations. This process of gravitational attraction continues to shape the universe's large-scale structure, pushing it towards an ever-developing, ever-expanding future. One of the most fascinating aspects of gravity is its ability to bend the very fabric of space and time. When light from distant galaxies passes near massive objects, such as galaxy clusters, it is bent and distorted by the gravitational pull of those objects. This phenomenon, known as gravitational lensing, allows astronomers to observe objects that would otherwise be invisible. By studying these distortions, scientists can uncover the hidden presence of dark matter, a mysterious substance that doesn't emit light, but exerts a gravitational pull on visible matter. Through the lens of gravity, the universe reveals itself in ways that challenge our fundamental understanding of the cosmos. Gravity not only shapes the structures of galaxies and clusters, but it also illuminates hidden aspects of the universe, giving us insight into phenomena like dark matter that would otherwise remain elusive. As we continue to study the universe, our understanding of gravity's role deepens. It is no longer just a force that governs the motion of planets or the fall of an apple from a tree. Gravity is the architect of the cosmos, shaping everything from the formation of stars to the grand organization of galaxies and beyond. The more we learn about gravity, the more we come to appreciate its central role in the cosmic dance that governs the evolution of the universe. However, quantum mechanics, with its intricate set of principles, offers an entirely distinct framework for understanding the behavior of subatomic particles. The two theories, quantum mechanics and general relativity, operate harmoniously within their respective domains, each excelling in the realms they were designed to describe. Yet, as we delve into regions where both gravitational and quantum effects interact, such as within black holes or in the moments immediately following the Big Bang, a profound clash arises between these two pillars of modern physics. The discordance between these theories presents a major challenge for scientists striving to form a unified theory that can explain both the quantum and the gravitational forces simultaneously. Another layer of complexity emerges when considering the very nature of gravity itself. While the force of gravity is familiar to us in everyday life, its true nature remains one of the greatest mysteries of science. Some researchers are exploring the possibility that gravity is not a fundamental force akin to electromagnetism or the strong and weak nuclear forces, but rather an emergent phenomenon. In this view, gravity could arise from deeper, more fundamental interactions that exist at the quantum level, far beyond the reach of current experimental capabilities. One particularly fascinating hypothesis is the existence of gravitons, hypothetical particles that would mediate the force of gravity in a manner similar to how photons mediate the electromagnetic force. Yet, despite the theoretical framework suggesting their existence, no experiment has yet managed to detect these elusive particles, and their existence remains unproven. The successful detection of gravitons would be a breakthrough in itself, confirming the quantum nature of gravity. Understanding gravity at the quantum level could have profound implications for our comprehension of the universe. A successful synthesis of quantum mechanics and general relativity could reveal hidden truths about the birth of the universe, the nature of black holes, the enigma of dark matter, and even the fundamental structure of space and time itself. As scientists continue to probe these unknowns, we stand on the edge of discoveries that could redefine our understanding of reality in ways that are currently unimaginable. The questions we ask now are pushing the boundaries of science into exciting new frontiers. Among the most recent and transformative developments in our exploration of the cosmos are gravitational waves, ripples in the very fabric of space and time, generated by some of the most cataclysmic events in the universe. These waves are produced by the violent collisions of massive objects, such as the merging of black holes or neutron stars. The first detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, marked a seismic shift in our understanding of astrophysics. Before this breakthrough, our knowledge of the universe was almost entirely limited to the study of electromagnetic radiation. light, radio waves, and other forms of radiation. Gravitational waves opened an entirely new way of observing the universe, allowing scientists to hear events that had been invisible to traditional telescopes. These waves provide an unprecedented opportunity to study the universe, especially phenomena that are too distant or faint to be detected by electromagnetic means. For example, the collision of two black holes can generate gravitational waves that carry information about their masses, spins, and even the distance between them. This information is invaluable as it offers insights into the properties and behavior of black holes, objects that are otherwise difficult to study with optical telescopes. By tracing the origins of these gravitational waves, scientists can determine the precise timing and location of cosmic events, providing a clearer understanding of the universe's history. This new form of observation opens up a treasure trove of data, enabling us to study the universe with a depth previously thought impossible. The fusion of gravitational wave detection with other forms of astronomical observation, such as electromagnetic radiation, has created a new paradigm known as multi-messenger astronomy. This approach allows scientists to piece together a more comprehensive picture of cosmic events. For instance, the simultaneous detection of a short gamma-ray burst and gravitational waves from a neutron star merger provides strong evidence that these two phenomena are intimately linked. Multi-messenger astronomy not only broadens our understanding of the cosmos, but it also fosters greater collaboration between astrophysicists, cosmologists, and other scientific disciplines, paving the way for deeper insights into the fundamental workings of the universe. As detection technologies continue to improve, the potential for new discoveries grows exponentially. Each new event observed adds another piece to the cosmic puzzle, advancing our knowledge of the universe's most mysterious and powerful phenomena. We are on the cusp of uncovering more profound secrets that could shape our understanding of the cosmos for generations to come. One of the ultimate goals of theoretical physics is the unification of gravity with the other three fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Currently, these forces are described by two different frameworks: general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, governs the behavior of gravity on large scales, influencing the movement of planets, stars, and galaxies. In contrast, quantum mechanics governs the subatomic realm, explaining the interactions of particles that make up the fabric of matter. The stark differences between these two frameworks pose a monumental challenge for scientists seeking a unified theory. If gravity could be unified with the other forces, it would represent a groundbreaking achievement, offering a single theoretical framework capable of explaining all physical phenomena. Such a theory, often referred to as a theory of everything, would have profound implications, potentially providing insights into the conditions that prevailed at the birth of the universe during the Big Bang, and perhaps even revealing new technologies based on the fundamental forces of nature. Currently, there are several promising theories that aim to bridge the gap between gravity and quantum mechanics. Among the most notable contenders are string theory and loop quantum gravity. String theory suggests that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can exist in more than the familiar 3 dimensions of space and 1 dimension of time, proposing additional hidden dimensions that could potentially integrate gravity into the broader framework of quantum mechanics. On the other hand, loop quantum gravity seeks to quantize space-time itself, suggesting that space and time are discrete at the smallest scales. This approach aims to reconcile general relativity with quantum mechanics by treating space-time as a dynamic, quantized entity rather than a continuous one. If successful, such a unification could provide new insights into black holes, dark matter, and dark energy, phenomena that are currently poorly understood and remain among the most profound mysteries in modern physics. We continue to explore the unification of gravity with other fundamental forces. Several groundbreaking experiments and technologies are poised to push the boundaries of our understanding. One of the most anticipated projects is the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory scheduled for launch in the 2030s. LISA will be capable of detecting gravitational waves from massive cosmic events, such as the merger of black holes or neutron star collisions, with unprecedented sensitivity. By placing 3 spacecraft in a triangular formation millions of kilometers apart, LISA will offer a level of precision that ground-based observatories cannot achieve, revealing new insights into the fundamental nature of space and time. Another ambitious initiative is the Einstein Telescope, a proposed underground facility designed to detect gravitational waves with even greater precision than current Earth-based observatories. By utilizing a network of interconnected tunnels, this observatory aims to reach deeper into the universe's history, capturing events and phenomena that are currently beyond the reach of existing instruments. The Einstein Telescope has the potential to revolutionize our understanding of black hole formation and evolution, offering new perspectives on the nature of gravity itself. The rapid advancements in computational modeling are also transforming the way we study gravitational interactions. With the rise of supercomputing and advanced visualization tools, researchers can now simulate cosmic events with remarkable accuracy. These simulations are not only crucial for verifying observations from telescopes, but they also serve as a guide for future research, helping scientists predict where gravitational phenomena might occur and design experiments to detect them. As these technologies continue to improve, the future of gravitational wave astronomy looks incredibly promising, offering the potential for even more groundbreaking discoveries in the coming decades. In recent years, we have seen a surge in quantum gravity initiatives, a field where researchers are striving to bridge the gap between the principles of quantum mechanics and the force of gravity. These pioneering efforts are pushing the boundaries of our understanding of the universe, possibly offering groundbreaking theories that could completely reshape our view of the cosmos at its most fundamental level. As these technologies and experiments evolve, they hold the potential to answer some of the most profound and long-standing questions regarding the nature of gravity, unveiling a universe that is even more complex, intricate, and awe-inspiring than we can currently fathom. At the heart of modern physics lies the theory of general relativity, which upended centuries of thinking about space and time. Unlike the conventional view, where time is seen as a constant ticking away uniformly across the cosmos, Einstein's theory reveals a far more flexible concept. Space and time are intertwined in a fabric known as spacetime. The presence of mass and energy causes this fabric to bend, shaping how gravity manifests throughout the universe. This groundbreaking perspective, introduced in the early 20th century, radically altered how we perceive both time and space. A crucial concept in general relativity is that time does not pass uniformly everywhere in the universe. The rate at which time flows is influenced by the strength of the gravitational field a person or object experiences. For instance, time moves more slowly closer to a massive object, such as a planet or a star, than it does in areas far from such gravitational sources. This effect, known as gravitational time dilation, has been confirmed through several experiments, one of which involved atomic clocks placed at different altitudes. The clocks placed at ground level, where gravity is stronger, ticked slightly slower than those placed at higher altitudes, where gravity is weaker. But gravity is not the only force that can affect the passage of time. The velocity at which an object moves through space also plays a significant role in how time is experienced. According to Einstein's special relativity, as an object approaches the speed of light, time slows down for that object relative to an observer who is stationary. In practical terms, this means that if you were traveling at a speed close to light in a spaceship, you would age more slowly than people who remained on Earth. While this concept may sound like science fiction, it is grounded in experimental data drawn from particle physics and satellite technology, where the effects of velocity time dilation have been observed. Within the framework of general relativity, time is not the constant, ever-ticking clock that we once thought it was. Instead, it behaves as a dynamic entity, shifting and stretching in response to gravitational forces and velocity. This idea of time's malleability reshapes our understanding of reality and challenges our most fundamental perceptions of the universe. As we continue to study and explore the intricacies of space-time, we are reminded that the universe we inhabit is far more complex than we may ever fully comprehend. Nowhere is this more evident than in the study of black holes, those enigmatic cosmic objects that continue to capture the fascination of physicists. Black holes are more than just colossal concentrations of mass. They are places where the very fabric of space-time is stretched to its limits. At the heart of a black hole lies what is known as a singularity, a point where gravity is so intense that the laws of physics, as we understand them, cease to function. This is where our conventional understanding of time and space is completely disrupted. As an object approaches the event horizon of a black hole, the boundary beyond which nothing, not even light, can escape, time appears to slow down dramatically for an external observer. However, from the perspective of someone falling into the black hole, time seems to proceed normally. This discrepancy is a striking example of how time is not an absolute, universal constant, but rather something that can be altered by the forces of gravity and relative motion. It raises profound questions about the nature of time itself. If time is so fundamentally shaped by the gravitational field near a black hole, what happens at the singularity, where gravitational forces become infinite? Does time even exist there? Theoretical physicists continue to ponder these questions, suggesting that the singularity could represent a state of timelessness. Current theories propose that space and time are not separate entities, but rather form an interwoven fabric that warps and stretches in response to mass and energy. As we continue to grapple with the mysteries of black holes and singularities, it is clear that these extreme conditions compel us to rethink the very structure of reality itself. One of the most tantalizing possibilities that arise from these insights is the idea that black holes might not be the final destination for information and matter. Some theories propose that black holes could serve as gateways to other regions of the universe, or even to entirely different universes. While these ideas remain speculative, they challenge our understanding of time, suggesting that time itself might not be linear or absolute. Instead, it might have no beginning or end, existing in ways we can scarcely imagine. As black holes continue to captivate the imagination of scientists and the public alike, they compel us to think about existence in a fundamentally new way. These cosmic giants not only draw us into the deepest corners of space, but also prompt us to confront some of the most profound questions about the nature of time and the universe. What is the true nature of time? Does it have a beginning or an end? Could there be alternative realities or even other universes where time behaves in ways we cannot yet comprehend? Ultimately, time, as we understand it, is far from a fixed or immutable concept. It is a dimension that can be shaped by the forces of gravity and the speed of motion. The presence of a massive object, such as a black hole, can cause time to slow down for those nearby, and the speed at which an object moves through space can similarly alter how time is experienced. As our understanding of the universe deepens, we are confronted with the realization that time is far more fluid and mysterious than we ever imagined, and its secrets are waiting to be uncovered. Time, as we experience it, is far from a simple, unchanging constant. Our perception of time can be deeply influenced by a variety of factors, not just the objective ticking of a clock. One significant influence is the age of the individual. For younger people, time seems to stretch endlessly, each year feeling like an eternity. For those older in age, however, time often feels like it passes in the blink of an eye. This discrepancy between the subjective experience of time and the scientific understanding of it highlights an intriguing divide, one between human psychology and the physical properties of time. Our perception of time is shaped by memory, emotion, and expectation, an ever-evolving phenomenon. This experience of time, though subjective, offers a powerful reflection of the broader mysteries of the universe. Our personal sense of time differs not only with age, but also with experience, cultural context, and individual life circumstances. The sensation that time speeds up or slows down is deeply intertwined with our psychological state, further emphasizing that time, while quantifiable, is also profoundly personal and elusive. On a grander cosmic scale, time behaves in ways that defy our conventional understanding. One of the most fascinating and challenging aspects of time is revealed through the concept of time dilation, a cornerstone of Albert Einstein's theory of relativity. According to this theory, time is not an absolute, immutable force that applies equally across the universe. Instead, it bends and shifts based on two primary factors: relative velocity and gravitational fields. Imagine two observers, one stationary on Earth, the other traveling in a spacecraft at nearly the speed of light. From the perspective of the Earth-bound individual, time passes normally. However, for the traveler, time moves more slowly. When they return home, the traveling twin will have aged much less than their sibling who remained behind. This scenario, often referred to as the twin paradox, serves as a striking reminder that time is not an independent entity, but is deeply connected to the movement of objects in space. Even gravity plays a role in the perception of time. Time moves differently depending on the strength of the gravitational field one is in. Clocks on the surface of the Earth, where gravity is strongest, tick more slowly than those in space, far from any massive body. This means that a clock positioned high in the mountains would actually measure time a fraction of a second faster than one at sea level. Though this difference is subtle on Earth in more extreme conditions, such as near a black hole, the effect of gravity on time is far more pronounced. This gravitational time dilation is not just a theoretical concept. It has practical implications. Satellites in orbit, such as those used in GPS systems, need to account for these tiny differences in time to maintain their accuracy. It's a fascinating example of how our understanding of time is continually tested by the universe itself, showing that time is not a rigid, universally agreed upon force, but a dynamic, fluid entity influenced by the very fabric of space and the forces that act upon it. Time dilation challenges the traditional human perception of time as fixed and linear. It reveals a universe where time behaves as malleable as space itself. The more we study the cosmos, the more we realize that time, in its fundamental nature, is not a constant but a fluid phenomenon, one that invites us to reconsider everything we thought we knew about the passage of time. Our journey into understanding time is far from over. As we explore deeper into the mysteries of space, particularly in relation to black holes and other cosmic phenomena, our comprehension of time could radically shift. For instance, as we study black holes, scientists have observed that time slows down significantly as one approaches the event horizon, the boundary beyond which nothing can escape. This curious slowing of time challenges our ideas of temporal progression, suggesting that near these immense gravitational forces, time itself may stretch and warp in ways we cannot yet fully understand. Similarly, if the quantum gravity waves theorized by physicists are ever confirmed, they could further unravel our current ideas about time. Quantum mechanics, which governs the behavior of particles at the smallest scales, may offer clues to the deeper, more complex nature of time, potentially linking it to the fundamental fabric of the universe. If time operates differently at quantum scales, it might mean that our linear understanding of time could be flawed, and events may be interconnected in ways that we have yet to comprehend. Such revelations would not only reshape cosmology, but could also transform our very understanding of our place in the universe. Moreover, the search for life beyond our planet could drastically alter how we perceive time on a galactic scale. If intelligent civilizations are discovered far beyond our solar system, it may require us to rethink not just how we experience time on Earth, but how time operates universally. The conditions that support life on other worlds, liquid water, stable energy sources, and essential chemical elements, might challenge our assumptions about the evolution of time and the processes that lead to life itself. Water, often referred to as the universal solvent, is crucial for life as we know it, facilitating countless biochemical reactions necessary for survival. But beyond water, life depends on certain chemical elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which combine in complex ways to form the molecules essential to life. These elements are abundant in the universe, particularly in the dust and gas found in stars and nebulae. This suggests that the building blocks of life may be widespread, and life itself may exist in forms we can scarcely imagine. In addition to the presence of these elements, a stable energy source is essential to sustaining life. On Earth, the sun provides the energy required for nearly all life forms. But energy can also come from other sources. For example, geothermal energy from volcanic vents on the ocean floor has been found to support life in environments that are completely devoid of sunlight. This opens up the possibility that life could exist in other parts of our solar system, such as on the icy moons of Jupiter and Saturn, where extreme conditions would seem to preclude life as we know it. As we look further into the cosmos and explore these questions, we are reminded of just how little we know. The potential for discovering life, understanding the true nature of time, and delving into the far reaches of the universe offers us an endless array of questions that challenge the way we think about reality itself. Every discovery, from the smallest quantum particles to the most distant galaxies, adds a new dimension to our understanding of time, space, and life, and forces us to reconsider the very nature of existence. What we know now is just the beginning. We cannot overlook the critical need for a stable environment in the quest for extraterrestrial life. Conditions on any planet or moon must allow for a temperature range that permits liquid water to exist and supports the chemical reactions necessary for life to thrive. This stability is not just about a consistent temperature, but also about the protective features a planet possesses, its atmosphere, magnetic field, and other safeguarding elements. These features are crucial for shielding potential life forms from harmful cosmic radiation and extreme temperature fluctuations. Without them, any hope of sustaining life is severely compromised. As we venture further into the exploration of exoplanets, planets orbiting stars beyond our own solar system, and as we continue to examine the diversity of environments within our solar system, we uncover a stunning array of possibilities for life beyond Earth. The field of astrobiology has become one of the most exciting frontiers of scientific discovery. Far from being a domain of mere speculation about little green men, astrobiologists are systematically investigating the myriad conditions that could support life elsewhere in the universe. Their work includes studying extreme environments here on Earth, such as the boiling springs of Yellowstone or the icy, desolate expanses of Antarctica, where life exists despite the harshest of conditions. These earthbound studies provide crucial insights into how life might emerge and survive in similarly unforgiving locations in space. One of the primary strategies within astrobiology is the search for planets that lie within the habitable zone of their respective stars. This is the region around a star where conditions may be just right for liquid water to exist, water being an essential ingredient for life as we know it. With the aid of advanced telescopes like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TS, astronomers have identified thousands of exoplanets, some of which lie in their stars' habitable zones. These discoveries are reshaping our understanding of where to focus our search for life beyond Earth. In addition to scanning distant worlds, current missions targeting our own solar system are providing critical data. Rovers like Perseverance, which explore the surface of Mars, are equipped with state-of-the-art instruments capable of analyzing soil and rock samples for organic compounds, key building blocks of life. Mars, with its history of liquid water, remains a central target in the search for signs of past or present life. Europa, one of Jupiter's moons, is another compelling destination. Beneath its thick icy crust, scientists believe Europa harbors a subsurface ocean, one that may have the chemical ingredients necessary to support life. As we plan missions to probe this intriguing world, we edge ever closer to understanding whether life could exist beyond Earth. Astrobiological studies do not exist in a vacuum. They draw on a wide range of disciplines, including geology, chemistry, and biology. By examining life's potential to thrive in extreme environments on Earth, and by exploring other planets and moons, scientists aim to answer one of humanity's oldest and most profound questions. Are we alone in the universe? This quest, filled with challenges and uncertainty, is as exhilarating as the discoveries themselves. Each step forward deepens our understanding, inspiring future generations to look up at the stars with wonder. The discovery of exoplanets, planets that orbit stars outside our solar system, has been a game changer in our understanding of life in the universe. Before the detection of these distant worlds, the idea of life elsewhere seemed purely speculative. Today, however, with thousands of exoplanets identified, many of which lie in the habitable zones of their stars, the dream of finding extraterrestrial life feels more plausible than ever. This expanding catalog of exoplanets reveals a breathtaking diversity of planetary systems. Some exoplanets are remarkably Earth-like, often referred to as Earth-like or potentially habitable, because they orbit within the habitable zone where temperatures could support liquid water. However, not all exoplanets share this comforting similarity to Earth. Many exhibit extreme conditions, such as gas giants with raging storms and uninhabitable atmospheres. This diversity only broadens our perspective, suggesting that life could adapt to a wider range of environments than we had previously imagined. In fact, the discovery of such variety has sparked fascinating discussions about the origins of life itself. By studying the atmospheres and surface conditions of exoplanets, scientists are beginning to piece together clues about how life might arise. For example, the detection of certain chemicals like oxygen or methane could indicate biological activity, much as they do on Earth. This burgeoning connection between chemistry and biology and astrobiology opens exciting new avenues of research. The idea that the very chemistry of distant worlds might mirror the processes that sustain life on Earth presents a tantalizing prospect for scientists. With each new discovery, we are challenged to rethink not only the possibility of life beyond Earth, but also the very nature of life itself. Could life be more adaptable and widespread across the universe than we previously imagined? These questions are propelling the field forward, inspiring new hypotheses and research that continually expand our understanding of life's potential throughout the cosmos. Ultimately, the discovery of exoplanets has sparked a paradigm shift in the way we approach the search for life. What was once a distant dream is now an active area of exploration. Each new exoplanet found provides us with new possibilities, fueling the imagination and driving the boundaries of scientific knowledge. As we expand our search, it is not just about finding other worlds, but also about redefining our own place in the vast, mysterious universe. With each discovery, we inch closer to answering the age-old question, are we alone? Despite these advancements, the journey is far from simple. Our current methods of detecting extraterrestrial life are still relatively rudimentary, with many challenges ahead. At present, most of our techniques focus on identifying specific biosignatures, chemical markers in the atmospheres of distant exoplanets that could signal the presence of life. Gases such as oxygen and methane are particularly promising, as they are often associated with biological processes. However, while these gases are strong indicators, they are not conclusive proof of life. These chemicals can also be produced by non-biological processes, meaning their mere presence does not guarantee that life exists on a distant world. In addition to looking for biosignatures, we continue to rely heavily on direct exploration. Space missions to planets and moons in our own solar system, such as Mars and the icy moons of Jupiter and Saturn, play a critical role in gathering evidence of life. Rovers and landers analyze soil and rock samples, seeking clues to past or present microbial life. However, much of this exploration remains confined to our immediate cosmic neighborhood. The vast majority of potentially habitable worlds lie far beyond our reach, making the search for extraterrestrial life a slow and painstaking process. Another major obstacle is the immense distances that separate Earth from these distant exoplanets. The technological limitations of our current space probes mean that even the nearest stars are many years, if not centuries, away. This delay in communication presents a significant challenge in the quest for life. Imagine sending a message to a distant planet and waiting decades for a response. That is the reality of interstellar communication, a frustrating but unavoidable barrier in our search for answers. Despite these challenges, the field of astrobiology continues to make strides. The search for life beyond Earth is far from over, and as technology advances, so too will our ability to explore and understand the cosmos. Every new discovery brings us one step closer to answering the question that has fascinated humanity for centuries. Are we truly alone in the universe? The concept of life itself, both a philosophical and scientific enigma, continues to challenge our understanding in profound ways. For millennia, humanity has defined life by the characteristics it exhibits on Earth: growth, reproduction, metabolism, and response to stimuli. Yet, the vastness of the universe suggests that life may not be limited to these familiar forms. Our search has been rooted in the assumption that extraterrestrial life might resemble the biological systems we know, life forms based on water and carbon, thriving in environments akin to those found on Earth. However, this is a narrow perspective. The reality is that life might manifest in ways far beyond our comprehension. In order to truly understand what life could look like on other planets, we must expand our definitions, embrace broader expectations, and acknowledge the limits of our current methods. The universe is immensely vast, and we have only begun to scratch the surface of its mysteries. The more we discover, the more we realize how much remains unexplored. As we peer into the cosmos, seeking signs of life beyond our own world, scientists have found themselves drawn to the most extreme environments on Earth. These extreme environments, places like the deep-sea hydrothermal vents, acidic hot springs, and the icy polar regions, host organisms that defy the boundaries of what we once thought possible. In these harsh and seemingly inhospitable places, life not only survives, but thrives. By studying these resilient organisms, we gain invaluable insights into the potential for life in extreme conditions elsewhere in the universe. Perhaps the most astonishing discovery has been the existence of extremophiles, organisms that can survive under conditions once considered uninhabitable. For instance, certain types of bacteria have been found living in the intense heat and pressure found at the ocean's deepest depths. Others flourish in environments with such high salinity that most organisms would perish. This adaptability suggests that life can exist in a much broader range of environments than previously imagined. If life can emerge in such extreme conditions here on Earth, there is no reason to rule out the possibility that similar organisms could be thriving on other planets with harsh characteristics. The oceans beneath the icy surface of Europa, one of Jupiter's moons, or the sulfuric clouds of Venus, may harbor life forms that, while completely alien to us, are no less alive. Furthermore, our research into extremophiles has provided us with a deeper understanding of the metabolic processes that could support life in environments vastly different from our own. These organisms often rely on unique biochemical pathways that enable them to extract energy from unconventional sources, such as sulfur, methane, or even hydrogen gas. Such insights push the boundaries of what we consider habitable environments. It's no longer enough to focus solely on the Goldilocks zone, the region around a star where conditions are just right for liquid water to exist. We now know that life may be able to thrive in places we once thought too extreme to support any form of biological activity. This shift in perspective doesn't just prepare us for the possibility of discovering extraterrestrial life, it also forces us to redefine what we consider to be life itself. Each discovery of life surviving in extreme environments on Earth broadens our understanding of the potential for life elsewhere in the universe. As we continue our search, these extraordinary organisms challenge us to rethink the limits of our imagination and our expectations. The universe is vast and full of unknowns, and as we look deeper into its expanse, we may find life where we least expect it. With each new revelation, the mystery of life continues to unfold, inviting us to explore ever further. As we continue this search, we must not forget that the universe is also home to many other mysteries, some of which challenge the very nature of our understanding of physics and the cosmos itself. One of the most profound and puzzling enigmas is dark matter. Although invisible to our eyes and telescopes, dark matter is thought to make up about 27% of the universe's mass. We infer its existence not by detecting it directly, but through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Despite decades of research, the precise nature of dark matter remains one of the greatest unsolved questions in modern astrophysics. Dark energy, another cosmic mystery, is even more elusive. It constitutes approximately 70% of the universe, yet we still do not understand its true nature. Observed primarily through its influence on the accelerated expansion of the universe, dark energy could either be a constant force inherent in space itself, or a factor related to gravity, an idea that scientists have yet to fully understand. This raises significant questions about the fate of the universe. Will it continue expanding forever, eventually leading to a cold and desolate expanse, or will gravity eventually pull it back together in a cosmic collapse? Then there are fast radio bursts, FRBs, which remain one of the most puzzling phenomena in modern astronomy. These bursts of radio radiation, which last mere milliseconds, release energy equivalent to that of the sun over several days. Discovered in the early 21st century, these FRBs appear to originate from distant galaxies, yet their exact cause remains unclear. Various hypotheses have been proposed, from the collapse of neutron stars to more exotic and far-reaching explanations, such as the possibility of alien technology. Each potential theory opens up even more questions, fueling both scientific inquiry and the public imagination. Finally, there's the theory of cosmic inflation, a brief period of exponential expansion of the universe that occurred right after the Big Bang. This theory helps explain the uniformity of the cosmos as we observe it today, but the mechanisms behind this rapid expansion remain elusive. To fully understand cosmic inflation could shed light on some of the most fundamental questions of the universe's creation and its eventual fate. These mysteries, dark matter, dark energy, fast radio bursts, and cosmic inflation, serve as constant reminders of how much we still don't know. Even in an age of remarkable scientific progress, the universe remains full of secrets waiting to be uncovered. Among the most intense and spectacular phenomena in the universe are gamma-ray bursts, GRBs. These catastrophic explosions release more energy in just a few seconds than the sun will emit over its entire lifetime. GRBs typically last only a few milliseconds to several minutes, yet they are so powerful that they can be seen from billions of light years away. These bursts are thought to occur during the death throes of massive stars, especially through the process of a supernova, where a star's core collapses into a neutron star or black hole. However, not all stellar deaths produce gamma-ray bursts. In fact, GRBs appear to require a very specific set of conditions, including extreme rotation rates and strong magnetic fields, factors that are still poorly understood. Traditional models of stellar evolution had assumed that massive stars would follow a predictable path, eventually ending in a supernova explosion, but without necessarily producing a gamma-ray burst. The fact that some supernovae result in these energetic outbursts while others do not has left scientists puzzled. What exactly is it that differentiates the conditions that lead to a GRB? This question remains a topic of intense research and debate, with astronomers exploring various possibilities, from the collapse of massive stars to the more exotic ideas involving black holes and accretion disks. Understanding the precise conditions that lead to gamma-ray bursts could illuminate not just the death of stars, but the broader processes that govern the life cycles of galaxies themselves. The search for life beyond Earth and the study of the mysteries of the cosmos challenges us in ways we have yet to fully comprehend. Each discovery raises new questions, revealing that there is much more to explore in this vast universe, some of which may surprise us beyond imagination. As we continue to look deeper, who knows what other groundbreaking revelations await? What we know for certain is that the universe is not only full of wonders, but full of questions. Questions that we may not yet be ready to answer, but ones that we are compelled to ask nonetheless. Furthermore, certain gamma-ray bursts, GRBs, have been found to have surprising relationships with specific types of galaxies, particularly those that are rich in younger stars. This discovery is challenging the long-held assumption that gamma-ray bursts originate exclusively from more massive stars in older galaxies. As a result, scientists are beginning to reassess the models that explain how these spectacular events are distributed across the vast timelines of the cosmos. This shift in understanding has led to a broader investigation into various stellar environments, prompting researchers to explore new dynamics that might be at play in these explosive phenomena. As the research continues to unfold, it's becoming clear that gamma-ray bursts are not just brief flashes of light, but rather key markers of how stars evolve, live, and ultimately die. These revelations are reshaping our understanding of stellar life cycles, with implications for how we view the early universe itself. Each breakthrough offers fresh insights into the processes that govern not only the birth and death of stars, but also the overarching forces that shape the cosmos. As astronomers refine their models to account for these new findings, they are uncovering a complex web of factors that can contribute to the formation of gamma-ray bursts. These discoveries are shedding light on the very fabric of cosmic history, offering us a clearer view of the processes that govern the evolution of the universe. In doing so, they continue to fuel human curiosity and drive the exploration of questions that have long puzzled us. How do stars form and die? What role do these massive explosions play in shaping the universe? And what mysteries still lie hidden in the vastness of space? Fast radio bursts, FRBs, a phenomenon that has captured the imagination of astrophysicists and the public alike, represent another of the great enigmas of modern astrophysics. These powerful and fleeting flashes of radio waves from distant galaxies occur in mere milliseconds, yet they carry an immense amount of information about the universe. The sudden and intense nature of these bursts has drawn the attention of scientists, prompting intense research into their origins and the processes behind them. One of the most intriguing aspects of FRBs is their uncertain origin. While some bursts have been traced back to specific galaxies, leading to theories that they are linked to phenomena such as neutron stars, pulsars, or even black hole activity, the exact mechanisms behind their creation remain unclear. Scientists continue to explore various hypotheses, with some speculating that these rapid bursts of energy could be markers of extreme cosmic events. Yet, despite years of study, the definitive cause of FRBs remains elusive, adding to their mystery and allure. What makes the study of FRBs particularly fascinating is the potential they hold for revealing unknown aspects of the universe. As researchers gather more data, they are increasingly focused on the distances these signals travel and the environments they pass through. Each burst offers a snapshot of the cosmic material it encounters on its journey, potentially unlocking critical insights into the distribution of matter in the universe. The real challenge, however, lies in determining how these signals can act as cosmic messengers, providing not just information about the bursts themselves, but also about the broader structures of the universe they traverse. The ongoing study of FRBs is not just an intellectual pursuit. It also challenges us to rethink our place in the cosmos. As scientists delve deeper into the nature of these mysterious signals, they are reminded of the vastness of the universe and our limited understanding of it. With every new burst detected, the quest to unravel the secrets of FRBs draws us closer to answering some of the most fundamental questions about the universe's structure and our place within it. Cosmic rays, the high-energy particles that continuously bombard the Earth from all directions, represent yet another critical frontier in our exploration of the universe. These rays, composed primarily of protons but also including heavier atomic nuclei and even electrons, originate from a variety of celestial sources, such as supernovae, black holes, and even our own sun. Despite their elusive nature, cosmic rays provide us with valuable clues about the extreme processes taking place in the cosmos. When cosmic rays interact with atoms in the Earth's atmosphere, they generate a cascade of secondary particles, which can be detected by ground-based instruments. By studying these interactions, scientists can glean information about the energy, ranges, and types of particles that exist in outer space, providing insights into the conditions present in the environments from which these rays originate. The highest energy cosmic rays, in particular, offer a window into some of the most energetic and dramatic phenomena in the universe, allowing researchers to formulate theories about how energy is transferred in cosmic magnetic fields. Beyond this, cosmic rays also serve as a kind of cosmic probe. Their journey through space allows them to reveal information about the fundamental properties of the universe, including the elusive nature of dark matter. Despite making up a significant portion of the universe's mass, dark matter remains invisible and difficult to detect. However, by studying how cosmic rays interact with the matter they encounter, scientists hope to learn more about the composition and dynamics of dark matter, potentially unlocking one of the biggest mysteries of modern astrophysics. In addition, cosmic rays also contribute to our broader understanding of fundamental physics. Their unpredictable nature challenges current theories, prompting new inquiries into how they interact with the fundamental forces of the universe. As scientists continue to analyze these particles, they are uncovering new contexts for exploring the limits of physics, pushing the boundaries of what we know about the universe. The study of cosmic rays is a powerful reminder of the interconnectedness of all things. These high-energy particles bridge the gap between the microcosm and the macrocosm, offering a unique perspective on the forces and phenomena that govern the universe. As our understanding of cosmic rays deepens, so too does our appreciation of the universe's complexity and our place within it. Anomalies in our observations of the cosmos serve as critical signposts, pointing us toward new possibilities and insights about the universe. When scientists encounter unexpected phenomena such as unusual star behavior, strange galaxy movements, or discrepancies in gravitational effects, these anomalies challenge our existing models and force us to reconsider our understanding of the cosmos. Rather than dismissing these peculiarities, researchers see them as invaluable clues that can drive further investigation and lead to new, groundbreaking discoveries. For instance, early observations of the motion of galaxies revealed speeds that couldn't be explained by the visible mass we could observe. This discrepancy led to the hypothesis of dark matter, a form of matter that doesn't emit light but exerts a significant gravitational pull. Similarly, the discovery of the accelerated expansion of the universe led to the hypothesis of dark energy, a concept that has fundamentally altered our understanding of cosmic dynamics. These developments highlight the critical role anomalies play in reshaping our cosmic narrative. By challenging established theories and prompting new lines of inquiry, these unexpected observations have led to some of the most revolutionary ideas in modern astrophysics. As we continue to explore the unknown, we are reminded that the universe is full of surprises, and that each anomaly has the potential to unlock new realms of understanding. Anomalies in the universe are not mere curiosities. They are catalysts for scientific collaboration and profound discovery. Physicists, astronomers, and mathematicians frequently join forces to investigate these unusual occurrences, each bringing a unique perspective that enriches the search for answers. These interdisciplinary efforts, fueled by a shared curiosity, allow scientists to refine and deepen their understanding of fundamental concepts like gravity, energy, and the fundamental forces that govern the cosmos. Every anomaly, whether a sudden deviation in data or an unexplained phenomenon, sparks a new line of questioning, urging researchers to probe deeper into the mysteries of the universe. What was once considered an outlier or an error in measurement often reveals the next great breakthrough in our understanding of the cosmos. As such, anomalies serve not as distractions but as essential drivers of scientific progress. They propel inquiry forward, urging scientists to examine the very fabric of the universe, ensuring that our theories evolve in tandem with our expanding knowledge. With each enigma we encounter, we embark on a journey of discovery, uncovering new layers of complexity and wonder in the vast expanse of space that we have yet to fully comprehend. Space is often envisioned as a vast, empty void, a seemingly endless expanse with little more than distant stars and galaxies scattered throughout. However, this image is far from accurate. Space is, in fact, a dynamic and intricate tapestry, teeming with hidden elements like dark matter, cosmic radiation, and countless particles and waves. The universe is not just a static backdrop for celestial bodies, but an active, interconnected system of forces, where galaxies, stars, and planets are bound together by the invisible threads of gravity. The study of space, its structure, its laws, and its unseen components is essential for answering some of the most fundamental questions about our place in the cosmos. To better understand the nature of space and the myriad phenomena it contains, scientists employ an array of advanced technologies. Ground-based telescopes allow astronomers to capture light across a broad spectrum of wavelengths, providing valuable insights into distant objects and events. Yet, despite their power, these telescopes are limited by the distortions caused by Earth's atmosphere, which can blur and distort the light they capture. To circumvent these limitations, space telescopes like the Hubble Space Telescope have been deployed, offering an unobstructed view of the universe by operating far beyond the reach of atmospheric interference. But telescopes are just one tool in the scientific arsenal. High-energy particle detectors and space probes play a critical role in expanding our knowledge of the universe's most elusive components. These instruments measure cosmic rays, magnetic fields, and even gravitational waves, ripples in the fabric of space-time caused by the collision of massive objects like black holes. Gravitational wave observatories, such as LIGO, Laser Interferometer Gravitational Wave Observatory, have opened up a new realm of discovery, allowing scientists to detect these subtle yet profound disturbances in space-time. These advancements not only expand our understanding of the visible universe, but also bring us closer to unveiling the mysteries of dark matter and dark energy, substances that make up the majority of the cosmos, but remain largely invisible to conventional observation. The study of space is a truly global endeavor, one that brings together experts from diverse fields, including astrophysicists, cosmologists, engineers, and data scientists. Their collective efforts, sharing observations, testing hypotheses, and refining models, continue to unravel the vast complexities of the universe. Each new discovery contributes a piece to the ever-growing cosmic puzzle, deepening our understanding and appreciation of the extraordinary beauty and complexity of space. Central to our evolving understanding of the universe is the concept of space-time, an elegant framework that combines the three dimensions of space, length, width, and height, with the dimension of time, creating a single four-dimensional continuum. This revolutionary concept, first articulated by Albert Einstein in the early 20th century, fundamentally altered our view of the universe. Traditionally, we think of space as a three-dimensional arena in which objects move and interact. But Einstein's theory of relativity introduced the idea that space and time are not separate entities, but are intertwined, forming a unified fabric in which every event is defined not only by its position in space, but also by when it occurs. Imagine a vast, infinite field of possibilities. To locate an object within this field, we need to know not just where it is, but when it exists within the timeline of the universe. This concept of space-time provides a richer and more complete description of reality, where time itself is as intrinsic to the universe as physical space. One of the most profound aspects of space-time is the way it reveals the relationship between time and gravity. Einstein's theory of general relativity posits that massive objects like planets and stars warp the fabric of space-time around them. This curvature influences the movement of other objects, dictating their paths through space. What we perceive as gravity is actually the result of objects moving along these curved paths. In this view, gravity is not a force pulling objects toward each other in the traditional sense, but the natural movement of objects along the bent landscape of space-time. For example, imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a dip in the sheet, and if you roll a smaller ball nearby, it will spiral toward the larger ball, not because it's being pulled directly, but because of the curvature created by the larger mass. This same principle governs the motion of celestial bodies. The Earth bends space-time around it, and the Moon, much less massive than the Earth, follows a curved path as it orbits our planet. Even light, the fastest thing in the universe, is affected by this curvature. Light passing near massive objects such as stars or black holes follows curved paths, an effect that can be observed in the bending of light from distant stars around our sun during a solar eclipse. This perspective of gravity and motion is a radical departure from earlier ideas, offering a completely new way of thinking about how objects move through space. It also invites us to reconsider our notions of time and movement in the cosmos. We are not simply traveling through space, we are moving through time as well. Understanding the full nature of space-time is one of the keys to unlocking the deepest mysteries of the universe, bringing us one step closer to a more complete comprehension of how everything in the cosmos is interconnected and how the fabric of reality itself operates. Furthermore, warped space-time introduces a plethora of captivating concepts, including the phenomenon of gravitational waves. These waves, often referred to as ripples in the fabric of space-time, are generated by the movement and acceleration of massive objects, such as the cataclysmic collision of black holes. The detection of these waves has revolutionized the field of astrophysics, unlocking new avenues of exploration that allow scientists to probe the universe in ways once thought impossible. By examining how mass, space, and time interact within the framework of warped spacetime, our understanding of fundamental cosmic processes is deepened. This includes everything from the intricate motions of celestial bodies to the grand evolution of the universe itself. The pursuit of more advanced theoretical models of space holds extraordinary promise for groundbreaking discoveries. Each new model developed is akin to a key that unlocks an ever deeper comprehension of the cosmos, shedding light on previously unimagined possibilities. These theories often venture into complex, uncharted territories, such as the nature of dark matter, the inner workings of black holes, or even the ultimate fate of the universe. By refining these models, scientists are able to propose scenarios that were once beyond the realm of possibility, inspiring bold new experiments and observations that can redefine our understanding of reality. One particularly thrilling area of exploration is the potential existence of multiple dimensions. Advanced theoretical models suggest that beyond the familiar three dimensions of space and one of time, there could be hidden dimensions that shape the very fabric of our universe. This concept opens the door to new insights into the fundamental forces of nature, potentially offering a unified theory that could connect gravity with the other basic forces. Such discoveries could not only enhance our grasp of particle physics, but they might also provide critical clues about the very structure of reality itself. These revelations could transform our view of the cosmos, offering a perspective that stretches beyond the limits of conventional understanding. Moreover, these theoretical frameworks can guide astronomers in their observations. Insights gleaned from advanced models can lead to more effective searches for exoplanets, those fascinating worlds that orbit stars outside our solar system. They might also refine our quest for extraterrestrial life by identifying the environments most likely to support life as we know it. The pursuit of these discoveries challenges the boundaries of what we consider possible and expands our understanding of the universe's potential. As we continue to refine our models, the advances may ultimately lead to entirely new technologies. Looking back through history, the understanding of electromagnetism directly contributed to the technological era we live in today, from communications to computing. In a similar vein, breakthroughs in space theories could inspire innovations in fields as diverse as materials science and energy production. These advances may propel humanity into a new age of knowledge and exploration, where the mysteries of the universe are no longer just subjects of theoretical debate, but tangible fields of study with profound practical applications. This is merely a glimpse into the vast potential that lies within the pursuit of advanced theoretical models. The journey ahead promises to be full of awe and wonder, offering revelations that have the potential to alter the course of human history. As we peer into the vast expanse of the universe, we begin to uncover a concept that, at first glance, seems almost paradoxical. The universe is continually expanding. This expansion has profound implications for our understanding of space over time. To fully appreciate the significance of this idea, it's important to realize that when we talk about space, we are not merely referring to the distances between objects. We are discussing a dynamic, ever-evolving fabric that stretches and shifts along with the universe itself. A helpful analogy is that of a balloon being inflated. As the balloon expands, every point on its surface moves away from every other point. In the same way, the universe is expanding, with galaxies acting like points on the surface of that balloon, moving farther apart as the universe grows. This means that the distances between galaxies are not constant. They stretch and change over vast astronomical timescales, fundamentally altering the nature of space itself. It is this stretching of space that defines how we perceive the universe's growth. It influences the fate of cosmic structures and, in turn, shapes the very nature of the universe's evolution. This expansion doesn't just impact the distances between galaxies, it also alters the cosmic backdrop against which all events unfold. Light from distant galaxies takes time to travel across the vastness of space, meaning we observe these galaxies not as they are today, but as they were millions or even billions of years ago. As the universe continues to expand, the light emitted by these far-off galaxies undergoes a phenomenon known as redshift, which makes them appear to move away from us. This redshift serves as a cosmic clock, enabling astronomers to map the history of the universe and the rate at which it has been expanding over time. The farther away a galaxy is, the faster it appears to be receding. This phenomenon provides compelling evidence of the dynamic and constantly changing nature of space itself. Understanding the universe's expansion is essential for grasping the broader narrative of cosmology, offering insights not only into the origins of the universe, but also into its future trajectory. As we delve deeper into these cosmic mysteries, we are not just uncovering the universe's past, but are also gaining a glimpse of what lies ahead. The concept of space shaped by expansion invites us to view the cosmos not as a static entity, but as a living, breathing force that is constantly evolving. A vast, uncharted frontier brimming with untold wonders waiting to be discovered. Galaxies, those magnificent and complex entities, are continuously evolving over the course of cosmic timescales that span billions of years. From their humble beginnings as small clumps of gas and dark matter, galaxies grow in complexity and size. The first galaxies formed as matter began to coalesce under the influence of gravity, giving rise to the first stars and stellar clusters. Over time, these stars age and die, enriching the surrounding gas with heavier elements through violent supernova explosions. This cycle of birth and death paves the way for future generations of stars, contributing to the stunning variety of structures we observe in the universe today. As galaxies evolve, their internal dynamics shift and their structures grow more intricate. These processes, spanning billions of years, offer a glimpse into the ongoing transformation of the universe, where even the most stable and seemingly eternal entities like galaxies are in a state of perpetual flux. The universe is not static. It is alive, constantly evolving, and its stories unfold in ways we are only beginning to comprehend. As galaxies evolve, they engage in complex interactions with one another, reshaping their structure and influencing the cosmic environment. These interactions can lead to dramatic events, such as mergers, where two or more galaxies collide and combine. The aftermath of such a collision is a profound transformation. The galaxies' shapes and sizes are altered, and their stellar populations undergo a fundamental shift. These galactic clashes can also ignite intense bursts of star formation, as the gravitational forces at play compress vast clouds of gas, triggering the creation of new stars at extraordinary rates. However, these galactic collisions are not rare events. In fact, they are a critical aspect of galaxy evolution and occur over vast stretches of time. The Milky Way, for example, our home galaxy, is on a predicted collision course with the nearby Andromeda galaxy. This cosmic merger is expected to unfold over the next 4 billion years, marking a dramatic chapter in the story of our galaxy's future. Galaxies are not only shaped by interactions with their neighbors, they can also transform due to internal processes. Over time, galaxies can exhaust their gas reserves, resulting in a slow decline in star formation. This phenomenon leads to the gradual aging of the galaxy, as older stars dominate the stellar population. This shift often causes galaxies to appear redder and more passive, with their once vibrant star-forming activity slowing down significantly. The movement and redistribution of gas within a galaxy play an essential role in its evolution, often influenced by the presence of supermassive black holes at the galaxy's center. These massive entities can have a profound impact on their surroundings. Through the release of energy into the galaxy, supermassive black holes regulate star formation in a process known as feedback. By controlling how gas is distributed and transformed within a galaxy, black holes help shape the path of galactic evolution. The story of galaxies is one of constant change, a dynamic dance of formation, interaction, and internal transformation. Galaxies grow, merge, collide, and sometimes even lose their gas, their evolution unfolding as a complex interplay of forces. This grand cosmic dance shapes the visible universe, continuously unraveling the mysteries of space and time. As we peer deeper into the cosmos, we gain new insights into the forces that drive this dynamic process. The formation and collision of galaxies are central topics in cosmology, filled with unanswered questions that intrigue scientists. One of the most significant unresolved mysteries is the precise mechanism behind galaxy formation. While models and theories explain how gas, dust, and dark matter come together to form galaxies, many details remain unclear. For example, what role do supermassive black holes play in this process? Understanding how these massive black holes influence their surroundings could provide crucial insights into the formation and growth of galaxies. Another intriguing question centers on galaxy collisions. When galaxies collide, they can merge, forming entirely new structures, or they may simply pass by each other, engaging in a gravitational interaction that alters their shapes and star formation patterns. Scientists are still working to understand why some galaxies collide more frequently than others and what factors drive these interactions. The role of dark matter in these collisions is a particularly important area of research, as dark matter seems to guide the gravitational forces that govern these galactic dances, though much about it remains a mystery. Furthermore, the fate of star formation during and after these galactic collisions adds another layer of complexity. When galaxies collide, the intense compression of gas clouds can trigger bursts of star formation. However, the exact conditions that determine whether star formation rates skyrocket or plummet are not fully understood. Researchers continue to explore the environmental factors and specific parameters that lead to these different outcomes. The timing and frequency of galactic collisions over the course of the universe's history also raise important questions. How often do these events occur, and how do they influence the morphological evolution of galaxies? As astronomers gather more observational data and refine their simulations, they hope to answer these questions, painting a more detailed picture of the universe's evolution. Each new discovery adds another piece to the cosmic puzzle and helping us better understand the forces that shape the universe. Galaxies, vast collections of stars, gas, and dust, do not exist in isolation. They are active participants in shaping the larger structure of the universe. Through gravitational interactions and collisions, galaxies undergo profound changes that not only affect their own evolution, but also influence the surrounding cosmic environment. One of the most significant ways in which galaxies contribute to the universe's structure is through galactic mergers. When two galaxies come close enough, their gravitational attraction can pull them together, leading to a spectacular collision. This interaction often sparks the formation of new stars, as the gas within the galaxies compresses and ignites. Over time, these mergers can lead to the growth of larger galaxies, thereby affecting the distribution of mass in the universe. Galactic clusters, which can house hundreds or even thousands of galaxies, are often formed as a result of these interactions. These vast structures stretch across hundreds of millions of light years and are key to understanding the large-scale architecture of the cosmos. In addition to mergers, galaxies can also exert tidal forces on one another. These forces may not result in a full merger, but can still have a profound impact on the shapes and properties of the involved galaxies. For example, when a smaller galaxy passes near a larger one, the gravitational pull can distort the smaller galaxy, stripping away stars and gas. This interaction can create stunning tidal tails or bridges of material between galaxies, while also triggering new regions of star formation. In some cases, tidal interactions can even stimulate the activity of supermassive black holes at the centers of galaxies, in bursts of energy that are observable across vast distances. The gravitational interplay between galaxies is a fundamental force that shapes the cosmic web. Through these interactions, galaxies contribute to the formation of clusters and superclusters, forming a vast network that defines the large-scale structure of the universe. Galaxies are not solitary entities. They are integral components of a much larger cosmic system. As they merge, collide, and interact, they weave a complex tapestry of cosmic evolution, continuing to unlock the mysteries of the universe. Galaxy clusters, immense assemblies of galaxies bound together by gravity, are among the most remarkable structures in the universe. These clusters are much more than just collections of stars and gas. They serve as laboratories for understanding the fundamental forces of nature. One of the most compelling reasons to study galaxy clusters is their potential to reveal the mysteries of dark matter. The majority of the mass within these clusters is composed of dark matter, an invisible substance that doesn't emit light or energy but exerts gravitational pull. By studying the movement of galaxies within clusters and observing the effects of gravitational lensing, where light from distant objects is bent by the cluster's gravitational field, Scientists can map out the distribution of dark matter. This research holds the key to unlocking one of the greatest enigmas of the universe, shedding light on the nature of dark matter and its role in shaping the cosmos. As astronomers continue to refine their techniques and gather more data, the study of galaxy clusters will remain at the forefront of cosmological research, offering invaluable insights into the hidden forces that govern the universe's evolution. Furthermore, galaxy clusters offer a fascinating window into the very evolution of the universe, providing invaluable insights into its vast history. These colossal structures are the final milestones in the cosmic journey of structure formation, marking where smaller clumps of matter have come together over billions of years. By delving into the characteristics of these clusters, such as their temperature and the energy emitted by the hot gases between galaxies, scientists can trace the intricate history of cosmic expansion. They can also identify the profound impacts of pivotal events like the Big Bang. Beyond just offering a glimpse into the past, galaxy clusters play a crucial role in testing cosmological theories. They act as essential benchmarks, enabling scientists to measure key parameters like the universe's rate of expansion and the density of matter and energy. By making precise observations of these clusters, researchers are refining our understanding of the universe's composition, ultimately helping to illuminate the mysteries of both our cosmic past and our future. Each new discovery about these gargantuan structures adds another critical piece to the grand puzzle of our existence within this infinite cosmos. To investigate the life cycles of galaxies, researchers employ a sophisticated combination of cutting-edge telescopes, cosmic simulations, and observational data. Space-based telescopes, such as the Hubble Space Telescope, allow astronomers to observe galaxies that are located across vast stretches of time and space. This is essential because light from distant galaxies can take billions of years to reach Earth, offering a glimpse into their ancient past. By analyzing the light from these far-off galaxies, scientists can infer their stage in the cosmic life cycle, whether they are still in their formative years, mature, or nearing their eventual demise. In addition to telescopes, computer simulations play a pivotal role in advancing our knowledge of galaxy formation and evolution. These simulations recreate the early universe's conditions, demonstrating how tiny fluctuations in matter density gave rise to the first stars and galaxies. By comparing the results of these simulations with actual observations, scientists can test and refine their models of cosmic evolution. These simulations not only shed light on the distant past, but also help predict how galaxies will evolve in the future, including phenomena such as galaxy mergers, star formation, and the subtle yet profound influence of dark matter. Another critical area of research involves understanding the fundamental materials that make up galaxies, namely gas, dust, and dark matter. These components play vital roles in shaping how galaxies form, evolve, and interact. For example, galaxies rich in gas are often more active in creating new stars. By studying a variety of galaxies, scientists can also gain insights into the different environments in which they exist, enriching our understanding of the diverse pathways in galactic life cycles. Ultimately, examining the life cycles of galaxies provides key insights into the broader story of cosmic evolution. It reveals how galaxies influence their surroundings, their role in recycling materials across the universe, and their contributions to the ever-expanding cosmic tapestry. Each discovery about these celestial giants illuminates the intricate relationships between galaxies, stars, and the very fabric of space-time itself. Looking to the future, the next wave of astronomical missions promises to further deepen our understanding of the universe. One of the most eagerly awaited projects is the James Webb Space Telescope, which has already begun its mission to capture the faintest light from distant galaxies. This powerful telescope, launched in December 2021, offers an unprecedented level of clarity and sensitivity, enabling astronomers to explore the history of the universe with a level of detail never before achievable. The insights provided by Webb will be crucial for understanding the formation of stars, planetary systems, and galaxies. Another landmark mission is the European Space Agency's launch of the Euclid satellite in 2023. Euclid's mission focuses on mapping the geometry of the dark universe, particularly dark energy, and dark matter. By mapping the distribution of galaxies across cosmic time, the satellite aims to enhance our understanding of how these mysterious forces shape the universe's expansion and structure. The data Euclid gathers will be instrumental in unraveling some of the most perplexing questions that have remained unsolved for decades. Additionally, the Nancy Grace Roman Space Telescope, set to launch in the coming years, promises to build upon the work of its predecessors. It will continue studying the universe's vast expanses while also exploring new frontiers in exoplanet research, focusing on planets beyond our solar system. Equipped with the ability to observe gravitational lensing and dark energy, the Roman Space Telescope will provide groundbreaking insights into the universe's most fundamental phenomena, contributing immensely to our understanding of cosmic mechanics. These missions represent just a fraction of the global efforts underway by scientists and engineers to answer some of humanity's most profound questions about existence and the nature of the universe. Each telescope, each satellite, is a stepping stone towards solving the mysteries of our existence and unlocking the secrets of the cosmos, offering new possibilities for discovery and understanding. As we stand on the precipice of these new endeavors, the universe continues to offer us clues about its origins and ultimate fate. The rapid pace of technological advancements is poised to revolutionize our comprehension of the universe in the near future. Imagine telescopes so advanced they can peer even further into space, observing events that were once beyond our reach. This increased capacity will allow us to gather even more detailed data on distant galaxies, revealing their behavior and formation processes in ways we never thought possible. Powerful new detectors will be able to capture faint signals from the early universe, offering a direct look into the conditions that existed shortly after the Big Bang. Moreover, breakthroughs in computation and artificial intelligence (AI) are reshaping the landscape of astronomical research. With the vast quantities of data flowing in from observatories worldwide, AI can now process and analyze this information with incredible speed, uncovering patterns and anomalies that would be impossible for humans to detect. These AI-driven discoveries could lead to major breakthroughs in understanding dark matter and dark energy, two of the most enigmatic and elusive forces that govern our universe. As these innovations continue to unfold, we are on the brink of a new era in our understanding of the cosmos, one that promises to answer questions we have pondered for centuries and reveal truths about our place in the universe that were once thought to be forever out of reach. The future of space exploration is brimming with potential, and the discoveries ahead are bound to reshape everything we know about the universe and our existence within it. Space exploration technology is undergoing an exciting transformation, with each new milestone bringing us closer to understanding the far reaches of our solar system and beyond. Missions to distant planets are no longer a mere dream, but an increasingly feasible reality. In the near future, we may send advanced probes to faraway worlds, each equipped with state-of-the-art instruments designed to gather invaluable data. These instruments could provide us with detailed insights into the composition of other planets, the nature of their atmospheres, and even potential signs of life. This kind of first-hand information could completely alter our perspective on what conditions are necessary to support life, not only on Earth, but throughout the cosmos. Equally remarkable is how advancements in portable technology are shifting the landscape of scientific discovery. With affordable tools and accessible platforms, amateur astronomers and citizen scientists are now able to contribute meaningfully to the field. What was once the domain of highly trained professionals in specialized labs has now been democratized. As a result, ordinary individuals are now empowered to make discoveries that may lead to groundbreaking theories or help confirm long-standing scientific concepts. This shift not only broadens the pool of contributors, but also accelerates the pace at which we gather knowledge, with everyday curiosity fueling extraordinary innovation. The accessibility of these technologies means that the wonders of space are no longer reserved for a select few, but are becoming a collective endeavor, uniting a global community of explorers. As we stand at the cusp of a new era of space exploration, it's important to recognize that humanity's reach now extends beyond Earth itself, stretching into the very fabric of the universe. This bold quest for knowledge and discovery, however, brings with it a host of ethical challenges that force us to confront our responsibilities as stewards of the cosmos. The exploration and potential colonization of other planets raise profound questions that extend far beyond the technical aspects of space travel. What does it mean to be caretakers, not only of our own planet, but also of other celestial bodies? How do we navigate the complexities of introducing human culture and structures to worlds that may already have their own, if unobserved, characteristics and systems? These questions compel us to consider whether we would, consciously or unconsciously, impose our own values on other planets, or whether we should engage in a manner that respects the potential for life and ecosystems that may exist. One of the most pressing ethical issues is planetary protection. As we venture further into space, there is a real risk that our exploration efforts could inadvertently disrupt ecosystems if they exist on other planets. The introduction of Earth-based microbes into an alien environment, such as the Martian surface, could have catastrophic consequences, eradicating potential native life forms before we even realize they exist. The potential for irreversible damage challenges us to think critically about the balance between the excitement of exploration and the responsibility we bear as interplanetary travelers. Would our ambitions to explore and colonize be worth the cost of destroying an ecosystem that may hold answers to profound questions about life beyond Earth? Furthermore, the possibility of colonizing other planets raises concerns about inequality. History is rife with examples of human exploration that were marred by exploitation and the imposition of over less powerful societies. The question is, as we extend our reach into the universe, how can we ensure that we do not replicate these troubling patterns? If a privileged few are able to establish settlements on distant worlds, could this create a divide not only between the people on Earth, but also between the new inhabitants of the cosmos? The dynamics of interplanetary inequality could introduce challenges of a scale we've yet to imagine, affecting not only social structures, but also the distribution of resources and opportunities in space. As we embark on this thrilling journey into the unknown, these ethical dilemmas are not merely abstract concerns, but real challenges that could shape the future of space exploration. Our ability to navigate these issues thoughtfully may very well define our legacy in the universe. It is not enough to simply reach out to the stars. We must do so in a way that reflects our highest values, balancing the drive for discovery with the need to respect the unknown and protect the integrity of the cosmos. In addition to the technological and ethical challenges, scientists also face the complex task of prioritizing which cosmic phenomena and questions to pursue. The universe is filled with mysteries, and deciding where to focus research is no small feat. This process is influenced by a variety of factors, ranging from the availability of cutting-edge technology to the shifting curiosities of the global scientific community. Often, the latest discoveries act as guideposts, pointing researchers toward new areas of inquiry. For instance, a breakthrough in our understanding of dark energy could prompt astronomers to redirect their efforts toward investigating how this enigmatic force affects the expansion of the universe. Technology plays a central role in shaping the course of scientific exploration. Advancements in instruments such as telescopes and particle accelerators can dramatically shift our focus. When new technologies emerge, they often open new doors to questions that were previously unreachable or unknowable. This ability to pivot quickly, taking advantage of new capabilities, means that scientists are constantly adjusting their priorities to match the evolving frontier of knowledge. Equally important is the spirit of global collaboration that characterizes modern scientific endeavors. Scientists from various disciplines and parts of the world are working together in ways that were once unimaginable. Research is no longer confined to isolated teams, but is increasingly characterized by a rich exchange of ideas and discoveries across borders. A breakthrough in one field can spark an entirely new line of inquiry in another, creating a dynamic interplay between fields such as astrophysics, biology, and chemistry. This collaboration is pushing the boundaries of our understanding, with researchers pooling their expertise to tackle questions that span the vastness of the cosmos. Together, these technological, ethical, and collaborative advancements are forging a new era of space exploration. What once seemed like the realm of science fiction is now becoming a tangible reality, expanding our understanding of the universe and our place within it. But with this new frontier comes the responsibility to tread carefully, ensuring that our curiosity does not overshadow our sense of responsibility. As we look to the stars, we must also look inward, examining the values that will guide us as we navigate the uncharted territory of the cosmos. Funding availability plays a crucial role in determining the direction and focus of scientific research. In many cases, the priorities of grant agencies and funding institutions heavily influence the types of research that get attention. These institutions often have specific themes or areas of interest that they aim to support, and this can dramatically reshape the landscape of scientific inquiry. For researchers, this means balancing their own passion for exploring the mysteries of the universe with the need to align their work with the funding priorities. As a result, the pursuit of answers to the most profound questions of the cosmos often intersects with the practicalities of securing financial support. This delicate balance influences the direction of cosmic exploration, which can shift rapidly in response to both new discoveries and changing societal interests. As our understanding of the universe evolves, so too do the questions that capture the collective imagination of both the scientific community and the public. Scientists, therefore, must be adaptable, ready to pivot as new data emerge or as funding priorities evolve. In doing so, they continue to explore the most pressing cosmic questions that will, ultimately, expand humanity's understanding of the universe. At the heart of modern cosmological research lies the study of cosmic backgrounds and foregrounds, two layers of information that provide vital clues about the universe's origins and its ongoing evolution. Cosmic background radiation, often referred to as the afterglow of the Big Bang, serves as a key to unlocking the early history of the universe. This radiation, which permeates the entire cosmos, represents a snapshot of the infant universe, offering a glimpse into its hot and dense beginnings. By studying the cosmic microwave background, CMB, radiation, scientists can learn a great deal about the universe's composition, its rate of expansion, and even the conditions that existed just moments after the Big Bang itself. Yet, while cosmic background radiation provides a critical window into the early universe, there is another layer of complexity that must be accounted for: cosmic foregrounds. These foreground signals come from a variety of sources, including our own Milky Way galaxy, nearby stars, and the interstellar gas that permeates the cosmos. These emissions can obscure or distort the clearer signals coming from the cosmic background radiation. Understanding and isolating these foreground signals is essential, as they can contaminate the pristine data that scientists need to analyze to gain accurate insights into the universe's origins. Thus, one of the primary challenges in cosmology is disentangling the cosmic background radiation from these foreground signals. By doing so, researchers hope to uncover a more accurate picture of the universe's history, revealing the forces and phenomena that have shaped the cosmos over billions of years. Through this complex process, scientists aim to answer some of the most profound questions in cosmology. What role do dark matter and dark energy play in the gravitational dance of galaxies? How did the first stars ignite, and what were the conditions that allowed galaxies to form in the early universe? Each new discovery in this field adds more pieces to the puzzle, but also generates even more questions. The universe seems to hold an almost endless series of mysteries, and with each breakthrough, researchers uncover more layers to explore. The knowledge gained through this study is not only critical to advancing our understanding of the cosmos, but also has the potential to unlock new realms of fundamental physics. These breakthroughs could one day challenge our current understanding of space, time, and the fundamental forces that govern the universe. As we peel back the layers of cosmic history, we come closer to understanding not just where we come from, but also where we might be headed. This quest to uncover the deeper truths of the universe is a journey that stretches the boundaries of human knowledge, offering a glimpse into the past, the present, and the potential future of our vast and mysterious cosmos. In addition to cosmic backgrounds and foregrounds, supernovae play a central role in the ongoing transformation of the universe. These stellar explosions are crucial to the chemical enrichment of the cosmos, acting as cosmic factories that produce a wide array of elements. When massive stars reach the end of their life cycle, they undergo a spectacular transformation, exploding in a brilliant display of light and energy that we recognize as a supernova. This explosion occurs when the star has exhausted its nuclear fuel and can no longer support its own weight, causing it to collapse under its gravity. The subsequent release of energy results in an explosion so powerful that it outshines entire galaxies. During their lifetimes, these massive stars fuse lighter elements such as hydrogen and helium into heavier ones, including carbon, oxygen, and iron. When the star explodes in a supernova, it scatters these newly created elements throughout the surrounding space. This is of immense significance because the materials ejected during a supernova become part of the gas and dust clouds that will eventually form new stars, planets, and other celestial bodies. These elements, critical to the formation of life as we know it, are thus distributed throughout the universe, enriching the next generation of stars and planets with the raw materials necessary for life. In this way, supernovae are not just destructive events, but rather essential processes that fuel the ongoing evolution of the universe. They are the forges in which the building blocks of life are created, and their explosive energy propels these elements across the cosmos, ensuring that the cycle of cosmic creation and destruction continues. As such, supernovae are integral to the story of the universe, marking both the end of one stellar life and the beginning of new possibilities for the formation of stars, planets, and life. Moreover, the energy released by supernova explosions plays a pivotal role in the continual formation of new stars. When these violent blasts unfold, their shockwaves ripple through the surrounding regions of the galaxy, compressing vast clouds of gas and dust. This compression triggers a cascade of events that culminates in the birth of new stars, initiating a cycle of stellar creation that spans across eons. In this way, the very elements generated in these cataclysmic explosions become essential building blocks for the formation of future stars and potentially even planets. This ongoing process contributes to the intricate chemistry that we observe throughout the universe today. In essence, supernovae act as both creators and distributors of the chemical elements that make up the universe. Without these dramatic stellar explosions, the cosmos would be a far simpler place, one devoid of the vast diversity of elements that form the foundation of planetary systems, including our own Earth. This intricate balance of life, death, and rebirth at the heart of the universe showcases the extraordinary processes that shape our cosmic environment. Indeed, the profound connection between these cosmic events is central to the very fabric of existence. One of the most enigmatic objects in the cosmos are neutron stars, which are the remnants of massive stars that have gone through the cataclysmic event of a supernova explosion. When a star that is at least 8 times more massive than our Sun exhausts its nuclear fuel, it succumbs to the force of gravity, collapsing inward. The outer layers of the star are expelled in a dramatic outflow, while the core is compressed into an incredibly dense state. This core transforms into a neutron star, an object with a mass greater than that of the Sun, all compressed into a sphere roughly the size of a city. The extraordinary density of neutron stars places them among the densest objects in the universe, sparking awe and fascination about the fundamental nature of matter. Neutron stars are primarily composed of neutrons, subatomic particles that carry no electric charge. In these stars, matter exists in an extreme state known as neutron degeneracy, where the neutrons are packed so tightly together that classical physics fails to describe their behavior. To understand how matter behaves in such environments, scientists must turn to quantum mechanics, which provides the only framework capable of explaining these phenomena. In such dense environments, neutron stars serve as natural laboratories for testing theories about the strong nuclear force, allowing physicists to explore the very limits of particle physics. Neutron stars are also known to exhibit extreme phenomena, including powerful magnetic fields that emerge during their formation. These magnetic fields can be more than 1 trillion times stronger than the most potent magnets on Earth. As a result, some neutron stars emit beams of radiation from their poles, which sweep across space like a cosmic lighthouse. These rapidly rotating neutron stars, known as pulsars, offer profound insights into the behavior of matter under extreme conditions. Their regular pulses of radiation provide scientists with remarkably accurate cosmic clocks, helping to measure time with extraordinary precision. Yet the mysteries of neutron stars extend beyond their fascinating external properties. The internal structure of these enigmatic objects remains a subject of intense research. Theorists speculate that the core of a neutron star might contain exotic particles such as hyperons or even quarks. Exploring these possibilities could unlock new realms of physics, taking us beyond our current understanding. Every new discovery about neutron stars not only deepens our knowledge of the universe, but also prompts further questions about the fundamental nature of matter and the forces that govern its behavior. Black holes and quasars, while vastly different in their nature, also wield a profound influence on their cosmic environments. At the core of every black hole lies an area where gravity is so intense that not even light can escape. This extraordinary gravitational pull affects everything within its reach, drawing in nearby gas, dust, and even stars. As matter gets too close to a black hole, it forms a swirling disk of material around it, which heats up due to the friction between particles. This immense energy release can generate powerful jets of particles that shoot outward, influencing the surrounding space far beyond the event horizon. Quasars, on the other hand, are brilliant and energetic regions surrounding supermassive black holes at the centers of galaxies. These supermassive black holes consume vast amounts of material, which causes the surrounding gas to accelerate and heat up. This intense heating process results in radiation emissions that are billions of times brighter than an entire galaxy. The energy emitted by quasars allows them to be visible across immense distances, offering a glimpse into the early universe. In addition to their staggering luminosity, quasars play a significant role in shaping the dynamics of their host galaxies. The powerful radiation from quasars can regulate star formation by preventing nearby gas from cooling and collapsing into new stars. Despite their destructive potential, black holes and quasars are critical agents of change in the universe. Their intense gravitational forces influence the formation and evolution of galaxies, often determining the fate of star formation. Some galaxies, influenced by the radiation and gravitational interactions from nearby black holes, may even experience a halt in star formation, becoming quiescent over time. Thus, while these cosmic entities may appear as destructive forces, they are essential for maintaining the delicate balance of their environments. The life cycle of stars is a remarkable journey, beginning with vast clouds of gas and dust that slowly condense under the force of gravity to form protostars. As these young stars develop, their mass determines the course of their evolution, leading to a variety of outcomes. However, many questions remain unanswered, particularly concerning the processes that govern the transition between these stages. One of the greatest mysteries lies in how medium-sized stars like our Sun will ultimately meet their end. We understand that these stars will eventually expand into red giants before shedding their outer layers. But the exact mechanics of this process are still unclear. Why do some stars lose their material more rapidly than others? What role do magnetic fields and rotation play in driving these mass loss mechanisms? Massive stars, which end their lives in spectacular supernova explosions, also present numerous unresolved questions. While we know that supernovae occur when the nuclear fusion within a star's core can no longer support its mass, the precise conditions that trigger these explosions remain uncertain. These events are vital as they scatter heavy elements into space, contributing to the formation of new stars and planets. Similarly, the formation of black holes remains a mystery. Do they form directly from the remnants of a supernova, or is there a more complex process involved? Understanding the life cycle of stars not only illuminates their eventual fate, but also provides key insights into the deeper workings of the universe. It offers a glimpse into the intricate interconnectedness of the cosmos, connections that we are only beginning to explore. As we gaze upon the night sky, the constellations above seem timeless, etched in their positions for eternity. However, they are far from static. The dynamic forces of the universe continuously reshape these cosmic patterns. One fascinating aspect of this celestial dance is the phenomenon known as stellar parallax. This refers to the apparent shift in the position of nearby stars as Earth orbits the Sun. This shift allows astronomers to measure the distances to these stars, helping us better understand their true locations within our galaxy. Over thousands of years, these subtle shifts can alter the shapes of constellations, transforming the patterns that we perceive in the sky. Far from being fixed, the constellations we observe are in constant flux, subtly reshaped by the ever-moving forces of the universe. Stars, while often thought of as immortal entities lighting up the night sky, are in fact far from eternal. They are born from the chaotic yet beautiful gathering of gas and dust, vast clouds of interstellar material that collapse under their own gravity. This birth process, called stellar formation, sets the stage for a star's life cycle, which, depending on the size of the star, can last millions to billions of years. But nothing in the universe truly lasts forever, and stars too eventually reach the end of their lives in magnificent and catastrophic displays. The death of a star, especially a massive one, often results in one of the most dramatic events in the cosmos, a supernova. In these explosive deaths, stars release an immense burst of energy and scatter elements into space, enriching the interstellar medium. These elements, such as carbon, oxygen, and iron, are the building blocks for future stars and planets. The remnants of a star's life can also evolve into objects like white dwarfs or neutron stars, depending on the mass of the original star. A white dwarf is the dense core of a star that has exhausted its nuclear fuel, while a neutron star is an even more compact and extreme object that forms when a star's core collapses under intense pressure. As stars undergo their transformations, their impact ripples through the cosmos, affecting not only the star systems they once dominated, but also the constellations they belong to. The shifting positions of stars over millions of years can subtly alter the shapes and patterns we see in the night sky, changing the constellations and even leading to the creation of new ones. This ongoing transformation reminds us that the universe is never static, but instead constantly evolving, with old patterns giving way to new formations. The Milky Way, our home galaxy, plays an important role in this cosmic dance. It is a spiral galaxy, densely packed with billions of stars. As the galaxy rotates, the stars within it move in relation to one another, their positions shifting over time. This dynamic motion of stars, constantly changing their locations within the vast expanse of the Milky Way, also shifts our perspective of the night sky. What we see now is just a snapshot, one moment in an ever-changing, grander narrative. Thus, while we take comfort in the familiar constellations that guide us through the night, the stars above are painting a constantly evolving canvas. The future may hold entirely new patterns in the sky, revealing themselves only as the universe continues its endless dance. The passage of time not only alters the stars themselves, but also our understanding of them. In the pursuit of knowledge, scientists are delving into some of the deepest mysteries of the universe, and some of the most fascinating discoveries are still on the horizon. One of the most puzzling and captivating concepts to emerge in recent years, the idea of dark energy. This mysterious force is believed to account for about 70% of the universe, and its presence is thought to be responsible for the accelerating expansion of the cosmos. Despite its profound influence, we know very little about dark energy. Its exact nature remains one of the greatest enigmas in modern physics. Researchers are working tirelessly to understand its properties and how it impacts the structures of the universe on a cosmic scale. Another area of deep exploration is string theory. This ambitious framework in theoretical physics proposes that the universe's fundamental building blocks are not point-like particles that as traditionally thought, but rather tiny vibrating strings. These strings vibrate at different frequencies, and their vibrations give rise to the variety of particles we observe. String theory offers a bold new way of thinking about the universe, suggesting that there may be extra dimensions beyond the familiar three of space and one of time. While we experience a four-dimensional reality, string theory posits the existence of up to 10 or even 11 dimensions, which could provide answers to some of the most profound questions about the forces of nature, including dark matter and dark energy. String theory also holds the potential to bridge two previously incompatible pillars of physics: general relativity, which governs the forces of gravity on a large scale, and quantum mechanics, which explains the behavior of particles at the smallest scales. For decades, scientists have struggled to reconcile these theories, but string theory may offer the framework needed to unite them into a cohesive understanding of the universe. This could in turn help explain phenomena like black holes and even the mysteries surrounding the very beginning of the universe, what happened during the Big Bang. Alongside these theories, quantum gravity is another exciting frontier in the search for a unified understanding of the universe. This theory seeks to merge quantum mechanics with general relativity, offering insights into the fundamental nature of gravity and space-time. A successful theory of quantum gravity could provide much-needed explanations for extreme cosmic phenomena, including black holes and the behavior of the universe at the birth of time itself. Speaking of black holes, these enigmatic objects continue to captivate physicists and cosmologists alike. Once thought to be simple points of infinite density, black holes are now understood to play a much more complex and critical role in the universe. Recent research suggests that black holes may not only be crucial to the formation and evolution of galaxies, but they might also hold the key to unraveling some of the most profound paradoxes in physics. One such mystery is the information paradox, which questions whether information that falls into a black hole is truly lost forever. Understanding how black holes operate could lead to a revolution in our understanding of the very fabric of reality. With these breakthroughs, scientists are inching closer to unraveling the mysteries that have eluded us for centuries. Each new discovery adds another piece to the puzzle of the universe, expanding the frontiers of knowledge and reshaping our view of the cosmos. And yet, despite all that we have learned, the true scope of the universe remains far beyond our grasp. What if I told you that everything we can observe accounts for just 5% of the entire universe? The remaining 95%, which includes both dark matter and dark energy, is completely invisible and largely incomprehensible. These elusive components shape the very structure of the universe, influencing galaxies, stars, and the very fabric of space-time itself. Dark matter, which constitutes about 27% of the universe, is one of the most mysterious substances known to science. Its name comes from the fact that it does not emit, absorb, or reflect light, making it invisible to conventional telescopes. Despite this, scientists know that dark matter exists because of its gravitational effects on visible matter. For example, the way galaxies rotate suggests that there is far more mass present than can be accounted for by the visible matter alone. Without dark matter, galaxies would not have the gravitational cohesion needed to stay intact. It plays a fundamental role in the formation of galaxy clusters and the cosmic web that connects them. Even though dark matter cannot be directly detected, its influence is undeniable. It is a driving force behind the large-scale structure of the universe, and without it, the cosmos as we know it would be entirely different. It holds the universe together, yet we know so little about it. This leaves us with a tantalizing puzzle. What is dark matter, and how does it interact with the visible universe? Then there is dark energy, the remaining 68% of the universe. This mysterious force is believed to be responsible for the accelerating expansion of the universe. While dark matter exerts gravitational pull, dark energy works in the opposite direction, pushing the universe apart. Together, dark matter and dark energy shape the evolution of the cosmos, but they remain one of the most profound, unsolved mysteries in science. What are they made of? How do they work? And most importantly, what role do they play in the ultimate fate of the universe? As scientists continue their quest to uncover the nature of these elusive forces, we are reminded that the universe is a vast, mysterious place. What we know is but a tiny fraction of what remains to be discovered, and each new piece of the puzzle brings us closer to understanding the universe in all its awe-inspiring complexity. Dark matter stands as one of the most perplexing and intriguing mysteries in modern science, fundamentally challenging our understanding of the universe. It pushes the boundaries of physics, urging researchers to rethink everything we thought we knew about the fabric of reality. While traditional laws of physics, grounded in the interactions of known particles, have served us well in explaining a vast array of cosmic phenomena, they fail to account for the peculiar behaviors seen in galaxies and galactic clusters. The existence of dark matter, though unseen and elusive, seems to be the only plausible explanation for these phenomena, presenting a gap in our knowledge that scientists are striving to fill. At its core, dark matter represents a puzzle that has remained largely unsolved, despite decades of investigation. Scientists have embarked on an ongoing search, conducting experiments both on Earth and in the far reaches of outer space. The goal is clear: to uncover the nature of this unseen force and understand what it's made of. Could dark matter be composed of exotic particles like weakly interacting massive particles, WIMPs, axions, or other hypothetical entities? These are just a few of the candidates researchers are investigating in their quest for answers. The search is nothing short of a journey into the very heart of the unknown, with the potential to reshape our understanding of the cosmos and our place within it. The theory of dark matter initially arose out of observations that challenged the very principles of gravity and mass. For years, scientists have speculated about the existence of a hidden mass that exerts gravitational forces on visible matter. This hypothesis is based on its gravitational effects, which can be seen in the way galaxies and galaxy clusters move through space. Despite the absence of any detectable light, heat, or radiation emanating from it, dark matter's presence is inferred from its ability to influence the motion of visible matter in space. Take the spinning of a galaxy, for example. When astronomers observe the outer stars in a rotating galaxy, they notice an anomaly. These stars are moving much faster than they should be, based on our understanding of gravity. According to Newton's laws, objects further from the center of a galaxy should move slower, as the gravitational pull weakens with distance. However, the stars on the outer edges of galaxies are moving at speeds far higher than predicted. This discrepancy points to the existence of additional mass that cannot be directly observed. It is as though there is an invisible gravitational glue holding these stars in motion, and that glue is dark matter. In addition to the study of galaxies, another compelling clue comes from the phenomenon known as gravitational lensing. This occurs when light from distant galaxies is bent around massive objects, like galaxy clusters. The amount of bending indicates the presence of mass that is not visible. By observing the bending of light, scientists can estimate the mass of these galaxy clusters, and once again, the data suggests that much more mass exists than can be accounted for by visible matter alone. This gravitational lensing effect serves as yet another piece of evidence for dark matter's existence. Furthermore, the study of the cosmic microwave background, CMB, the faint glow left over from the Big Bang, provides more insight. Observations of the CMB reveal fluctuations that correspond to varying densities of matter in the early universe. These fluctuations suggest that visible matter forms only a small fraction of the total density of the universe, supporting the hypothesis that a large portion of the universe's mass is invisible and made up of dark matter. Simulations of cosmic structure formation also lend credence to the theory of dark matter. When computer models are run to simulate the formation of galaxies and other large-scale cosmic structures, including dark matter in the simulations, leads to results that closely match our actual observations of the universe. Without dark matter in these models, the structures do not form in the same way, which suggests that this invisible substance is a crucial factor in the formation and behavior of galaxies and clusters. Despite this overwhelming evidence, dark matter remains invisible to our most powerful instruments. It accounts for about 25% of the total mass and energy content of the universe, yet we cannot directly observe it. As a result, scientists continue to hunt for the elusive particles that could explain its nature. The leading candidates fall into two major categories: WIMPs, weakly interacting massive particles, and axions. WIMPs are perhaps the most popular contenders. These hypothetical particles are predicted by certain theories in particle physics and would have mass. What makes them so intriguing is their ability to interact through the weak nuclear force. This means that WIMPs would not interact in the same way that ordinary matter does, making them extremely difficult to detect. Their weak interaction with normal matter allows them to pass through it almost effortlessly, giving rise to their nickname, ghost particles. Around the world, sophisticated experiments are being conducted to detect these elusive particles and confirm their existence. Another intriguing possibility is the axion, a much lighter particle, hypothesized in theories that attempt to unify the fundamental forces of nature. If axions exist, they could explain certain puzzles related to the strong nuclear force that governs interactions within atomic nuclei. Much like WIMPs, axions would interact very weakly with other matter, making them incredibly elusive. If experiments designed to detect axions succeed, they could reveal entirely new aspects of the universe and further our understanding of dark matter. Beyond WIMPs and axions, there are other candidates that merit attention, such as sterile neutrinos or even primordial black holes. Each of these offers a unique explanation for the mystery of dark matter, and ongoing research into these possibilities continues to expand our horizons. The hope is that one day, a breakthrough discovery will provide the key to unlocking the true nature of dark matter, ultimately transforming our understanding of the universe. As research progresses, we are learning that dark matter has a profound influence on the structure and behavior of galaxies. Even though we cannot see it, its gravitational pull is a dominant force in shaping the cosmos. When we look at a galaxy, what we observe is only a small fraction of its total mass. Stars, gas clouds, and other visible matter are all that we can detect with our instruments. Yet these constitute only a fraction of the mass that is needed to explain the galaxy's behavior. The rest, we now know, is likely dark matter. This invisible mass acts as a scaffolding, holding galaxies together and influencing their rotation. In a typical galaxy, the visible matter, the stars, gas, and dust, is much less than what is required to explain the observed rotation speeds of the galaxy's outer stars. According to classical physics, stars farther from the center of a galaxy should move more slowly because they experience a weaker gravitational pull. However, in reality, these stars move at much higher speeds than expected. This discrepancy can only be explained if there is additional mass, dark matter, exerting gravitational forces on these distant stars. Essentially, dark matter forms a vast, invisible halo around galaxies, extending far beyond their visible edges. This halo provides the necessary gravitational influence to keep galaxies from flying apart, offering further evidence that dark matter plays a crucial role in the formation and maintenance of galaxies. While scientists have yet to uncover the full nature of dark matter, it is clear that this mysterious substance is integral to the structure of the universe, and our continued exploration of it may one day provide answers that reshape the very foundations of physics. Furthermore, dark matter plays an indispensable role in the formation and evolution of galaxies, acting as a silent architect behind the cosmic structures we observe today. In the earliest moments of the universe, subtle fluctuations in the density of matter caused tiny regions to clump together, forming the building blocks of galaxies. These gravitationally bound regions, enriched by dark matter, became the seeds around which gas, dust, and stars gathered, ultimately coalescing into the galaxies that populate our universe. Dark matter was not merely a passive participant in this process. It was the unseen force that shaped the paths of galaxies, guiding their formation and evolution across vast stretches of time. As galaxies collided and merged, dark matter played a pivotal role in dictating the dynamics of these celestial events. It influenced the motion of stars and gas within galaxies, affected how galaxies interacted during mergers, and contributed to the large-scale structures of the cosmos. In fact, the distribution of dark matter within these structures is what gives rise to the very framework of the universe. In our quest to understand the intricate dance of galaxies and their evolution, dark matter remains a key ingredient, integral to the grand cosmic recipe. The study of dark matter is not confined to theoretical musings. It is an active area of research, with scientists employing cutting-edge technology to unravel its mysteries. Observatories like the Atacama Cosmology Telescope and various satellite missions are pivotal in shedding light on dark matter's elusive properties. These instruments probe deep into the heart of the cosmos, capturing detailed observations that can offer insights not just into the galaxies we see today, but also into the deeper nature of the universe itself. By exploring the impact of dark matter on galactic evolution, researchers are unveiling secrets about the history of the cosmos, offering glimpses into the forces that have shaped the structure of the universe and our place within it. Dark matter is not just a passive player in the cosmic drama. It is a fundamental force that has shaped the universe since its inception. Though it cannot be seen directly, its presence is felt in the gravitational effects it exerts on visible matter. This invisible substance accounts for about 27% of the total mass and energy content of the universe, yet it continues to evade direct detection. The pursuit of understanding dark matter is one of the most challenging and exciting frontiers in modern physics. Scientists are developing innovative techniques to detect this elusive substance, which promises to transform our understanding of the universe. Around the world, experiments are being conducted to detect dark matter's subtle interactions with ordinary matter. One of the most significant efforts in this regard is the Large Underground Xenon, Lux Zeppelin, experiment located deep beneath the surface in South Dakota. This facility uses a massive tank filled with liquid xenon, hoping to capture the faint signals produced when dark matter particles interact with regular matter. If dark matter interacts with visible matter, it may produce small flashes of light or ionization, which are detectable by sensitive equipment. The underground location of the Lux Zeppelin experiment shields it from cosmic rays and other background noise, significantly improving the chances of detecting these rare and elusive interactions. In Europe, another ambitious experiment is making strides in the hunt for dark matter. The cryogenic rare event search with superheated terrestrial detectors, CREST-T uses tiny crystals to detect the energy deposited by interacting particles. When a dark matter particle collides with these crystals, it generates a tiny amount of heat, which scientists can measure. This technique is part of a broader effort to harness cryogenic technologies and advanced sensors to probe the nature of dark matter in unprecedented detail. International collaborations have also led to the creation of experiments like the PandaX project in China. Using similar principles to those employed by Lux Zeppelin, PandaX aims to detect dark matter interactions in a highly sensitive and controlled environment. Each of these experiments shares a common goal: to create the optimal conditions for observing the extremely rare interactions between dark matter and ordinary matter. As researchers continue to refine their methods and technologies, the possibility of directly detecting dark matter becomes ever more tangible, offering the promise of uncovering the secrets of one of the universe's most fundamental and enigmatic components. In addition to dark matter, another mysterious force continues to captivate the attention of scientists: dark energy. Dark energy is thought to make up approximately 70% of the universe's total energy content, and it is responsible for the accelerated expansion of the cosmos. Despite its ubiquity, however, dark energy remains largely theoretical, with little direct evidence of its properties. Scientists believe that dark energy has a repulsive effect, pushing galaxies further apart and altering the course of cosmic evolution. This discovery, made in the late 20th century, radically transformed our understanding of the universe and its fate. While dark energy is thought to be driving the expansion of the universe, dark matter serves a different function. Dark matter constitutes about 25% of the universe's mass and acts as a gravitational glue that holds galaxies and clusters of galaxies together. Unlike dark energy, which accelerates the expansion of the universe, dark matter exerts a gravitational pull that influences the movement and formation of galaxies. Though dark matter cannot be observed directly, scientists can infer its presence from the way galaxies rotate and interact. The fundamental difference between dark energy and dark matter lies in their opposing effects on the universe. Dark energy accelerates the expansion of space, pushing galaxies apart, while dark matter works to keep galaxies bound together, serving as the scaffolding for cosmic structures. Understanding both dark matter and dark energy is crucial for developing a comprehensive picture of the universe. These two phenomena shape the structure and evolution of the cosmos, yet they operate in fundamentally different ways. As research into both dark matter and dark energy progresses, scientists continue to probe the depths of these mysteries, seeking to uncover the forces that govern the universe's past, present, and future. Each new discovery adds another piece to the puzzle, deepening our understanding of the cosmos and our place within it. The discovery of dark energy was a watershed moment in the history of cosmology, profoundly altering our understanding of the universe's expansion. Before this revelation, scientists believed that the universe's expansion was slowing down, primarily due to the gravitational pull of matter, both visible and dark. However, the discovery that the universe's expansion is accelerating rather than decelerating has forced scientists to reconsider their models of cosmic evolution. This unexpected finding opened up a new chapter in the story of the universe, one that is still unfolding as researchers continue to explore the implications of dark energy and dark matter for the fate of the cosmos. However, in the late 20th century, astronomers made a groundbreaking discovery that would alter the course of our understanding of the universe. Observations of distant supernovae revealed an unexpected and puzzling phenomenon. Instead of the universe's expansion slowing down over time, it was accelerating. This acceleration suggested the presence of an invisible, mysterious force known as dark energy. Though it remains one of the most elusive and enigmatic aspects of modern cosmology, dark energy is believed to make up about 70% of the total energy content of the universe. Despite its dominant presence in the cosmos, dark energy's true nature is still shrouded in mystery. Unlike gravity, which pulls matter together, dark energy works in the opposite direction, pushing galaxies apart and driving the rapid acceleration of the universe's expansion. This discovery forced cosmologists and astronomers to reevaluate the fate of the universe itself. Models that once suggested a universe gradually slowing down due to gravitational forces now give way to a more complex picture. A continually expanding cosmos, one whose fate may be shaped by forces far beyond our current understanding. The implications of dark energy stretch far beyond theoretical speculation. This invisible force is not merely an abstract concept. It is an essential and fundamental aspect of how the universe operates on large scales. Understanding it forces scientists to confront questions about the very fabric of space and time. Is dark energy a constant, unchanging force, or does its influence fluctuate over time? Could it be linked to modifications in our understanding of gravity, or perhaps even the presence of additional dimensions that we have yet to detect? These questions challenge the foundations of physics and could lead to a profound shift in our understanding of the laws that govern the universe. One of the most commonly discussed scenarios resulting from dark energy's presence is the idea of a universe that expands indefinitely. In this scenario, galaxies would continue to drift apart, slowly growing farther from each other with no end in sight. Over time, this expansion could cause the universe to grow increasingly cold and dark, reaching what scientists refer to as heat death. This is a state in which energy is evenly distributed across the cosmos and no processes are left to sustain life or light as we know them. The potential reality of a heat-dead universe raises profound existential questions about the long-term fate of everything within it, from stars to galaxies to life itself. Beyond its role in the expansion, dark energy also prompts further inquiry into the very structure of the universe. Could its effects be connected to other cosmic phenomena, such as the elusive nature of dark matter or the behavior of space-time itself? As scientists probe deeper into the mysteries of dark energy, they face the possibility that the very laws of physics, as we understand them, may need to be rewritten. This realm of inquiry is one of the frontier mysteries of science, a vast and uncharted territory that invites both fascination and intense scrutiny as we continue to unravel its many secrets. The existence of dark energy and its role in accelerating the universe's expansion is supported by multiple key pieces of evidence collected through careful and precise astronomical observations. One of the most important pieces of evidence emerged in the late 1990s, when two independent teams of astronomers discovered something unexpected about the behavior of distant supernovae. These stellar explosions, which marked the death of massive stars, appeared much dimmer than anticipated. This dimness indicated that the supernovae were farther away than previously thought, which in turn suggested that the universe was expanding at an accelerating rate. This was a clear sign of dark energy's influence, adding a powerful piece of evidence to the growing body of research pointing toward its existence. Another significant source of evidence comes from the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. By analyzing the temperature fluctuations in this ancient radiation, scientists have been able to map the large-scale structure and composition of the universe. Observations from missions like the Wilkinson Microwave Anisotropy Probe, WMAP, revealed that dark energy constitutes about 70% of the universe's total energy content. This data aligns with the idea that dark energy is not a peripheral or minor influence, but rather a central component in the expansion and evolution of the cosmos. In addition to these direct measurements, large-scale surveys of the universe's structure, such as those examining the distribution of galaxies across vast cosmic distances, have provided further evidence for dark energy. By studying how galaxies cluster and interact with each other, researchers have been able to infer the dynamics of cosmic expansion. These surveys have shown that the rate at which cosmic structures grow aligns with a model that incorporates dark energy, further reinforcing the idea that dark energy is a significant force at play in shaping the universe's evolution. Gravitational lensing, the bending of light from distant galaxies around massive objects, offers yet another layer of evidence. This phenomenon occurs due to the warping of space-time by gravity, but it also provides important insights into the overall density and geometry of the universe. Observations of gravitational lensing have been consistent with predictions that include dark energy, further highlighting its pervasive influence on the universe's structure. Together, these pieces of evidence help scientists piece together a more complete picture of the universe, one in which dark energy is not just a theoretical concept, but a central force shaping its past, present, and future. By studying these observations, cosmologists are beginning to understand how dark energy drives the universe's accelerated expansion, but many questions remain unanswered. As they probe deeper into these mysteries, they may uncover new insights that not only reveal the true nature of dark energy, but also redefine the very laws of physics. In the early universe, shortly after the Big Bang, a fascinating phase known as cosmic inflation occurred. This brief period of exponential expansion saw the universe grow at a truly astonishing rate, from subatomic scales to a size vast enough to allow the first particles to form. During inflation, irregularities in the universe's density were smoothed out, which led to the uniform cosmic background radiation that we observe today. But what powered this incredible growth? Some scientists believe that dark energy may have played a crucial role during this period, similar to its influence in the current epoch. During cosmic inflation, the universe's rapid expansion was driven by a field that exerted a repulsive effect on gravity, allowing space itself to stretch at an unprecedented rate. The connection between this inflationary field and dark energy is a tantalizing possibility. Could dark energy be an extension of the same principles that governed the inflationary period, now operating on a much larger cosmological scale? After the inflationary phase, the universe began to cool, and matter started to clump together under the influence of gravity. However, the influence of dark energy did not disappear. It gradually became more apparent, especially in the later stages of cosmic evolution. This shift led to the current understanding that the universe is not just expanding, but its expansion is accelerating, a realization that emerged only in the latter half of the 20th century. Essentially, both the early inflationary period and the current phase of cosmic expansion share a fundamental similarity. Both are driven by a field that exerts a force on the fabric of space-time itself. While cosmic inflation set the stage for the universe we see today, dark energy's influence is now reshaping the future of the cosmos in ways that continue to challenge and expand our understanding of the universe and the forces that govern it. Dark energy is the mysterious force that is driving the expansion of the universe, ensuring it continues to accelerate at an ever-increasing rate. This phenomenon raises profound questions about the ultimate fate of the cosmos, intertwining the past and future of cosmic evolution. As we peer deeper into the fabric of space-time, we are confronted with a grand cosmic puzzle that beckons us to explore the deeper mysteries that lie at the heart of the universe's architecture. As scientists continue to delve into the enigma of dark energy, they are uncovering startling revelations. It is believed that dark energy makes up approximately 70% of the universe, an overwhelming portion of the cosmos that remains largely invisible to our current observational tools. While it is credited with pushing the universe apart, it has baffled scientists who are still searching for its true nature. But within this uncertainty lies the spark for alternative theories, which may help us rethink what we know about the fundamental forces of nature. One of the most compelling alternatives to the dark energy model is the theory of modified gravity. This concept proposes that the laws of gravity, as formulated by Isaac Newton and later refined by Albert Einstein, may not be as universally applicable as we once thought. On vast cosmic scales, gravity might behave differently, particularly when it interacts with enormous distances or large masses. Some models even suggest that these alterations in gravitational behavior could account for the accelerated expansion of the universe without the need for dark energy. If true, this would completely transform our understanding of gravity, leading to a reevaluation of one of the most fundamental forces that govern the cosmos. Another theory that scientists are exploring involves the idea of dynamic dark energy. While traditional models treat dark energy as a static, unchanging force, dynamic dark energy suggests that this mysterious component of the universe could evolve over time. This shifting nature of dark energy could offer a fresh perspective on the expansion of the universe, challenging the notion of a constant force. If dark energy is indeed influenced by factors such as the distribution of matter in the universe or the history of cosmic expansion, then the rate at which the universe expands could vary in ways that we have yet to fully understand. In this ever-evolving landscape of theoretical physics, one more intriguing possibility is the concept of a multiverse, where our universe is just one of many, each governed by its own set of physical laws. In such a framework, dark energy might not be an intrinsic property of our own universe at all. Instead, it could be the result of living in a universe with a unique set of conditions that give rise to this force. This perspective not only raises profound questions about the true nature of dark energy, but also invites us to consider the existence of other realities beyond our own. Are we a part of a larger cosmic ensemble, where every universe unfolds according to its own set of rules? The potential implications are staggering. As the scientific community continues its quest for answers, these alternative theories may reshape our understanding of dark energy, the forces that govern the universe, and even the very fabric of reality itself. Meanwhile, in another corner of the cosmos, there lies an even more puzzling phenomenon: black holes. These enigmatic objects are among the most fascinating and mysterious entities in the universe, yet we have compelling evidence of their existence despite the fact that they are invisible to the human eye. The key to detecting black holes lies not in observing them directly, but in studying the effects they have on the surrounding matter. Black holes exert an immensely powerful gravitational force that influences the motion of nearby stars and gas. For example, astronomers have tracked the orbits of stars as they circle an invisible mass at the center of our galaxy, the Milky Way. The movement of these stars suggests the presence of a supermassive black hole, a discovery that has transformed our understanding of the galactic center. The behavior of these stars, in fact, serves as one of the strongest pieces of evidence for the existence of black holes, showing that something unseen and extraordinarily dense is shaping their orbits. In addition to gravitational effects, black holes reveal themselves through the intense radiation emitted by matter as it falls into them. This process, known as accretion, occurs when gas and dust spiral inward, becoming heated to extreme temperatures. The energy released during this spiraling journey creates high-energy X-rays, which can be detected by specialized telescopes equipped with X-ray detectors. These bursts of radiation provide astronomers with vital information about black holes, revealing the inner workings of their accretion disks and allowing us to observe their immense power from afar. Yet, the true nature of what happens inside a black hole remains a profound mystery. Once matter crosses the event horizon, the point of no return, it is drawn inexorably toward the black hole's singularity, a point of infinite density. Here, the normal laws of physics break down and current models of spacetime cease to function. This boundary, the event horizon, marks a dramatic shift in the behavior of matter and energy, pushing our understanding of the universe to its limits. The fate of matter inside the event horizon remains one of the greatest unsolved problems in physics, challenging everything we know about the fundamental nature of space and time. Moreover, the black hole information paradox further complicates our understanding. According to the principles of quantum mechanics, information about a system cannot be lost, but what happens to the information that falls into a black hole? Some theorists believe that this information is encoded on the event horizon itself, while others speculate that it might be released in some form as the black hole evaporates, a process predicted by the legendary physicist Stephen Hawking. This paradox forces scientists to confront the limits of our current theories, particularly when trying to reconcile gravity, quantum mechanics, and thermodynamics. Despite these challenges, the study of black holes offers us a glimpse into the heart of the universe's deepest mysteries. Their existence challenges our most basic assumptions about reality and forces us to reconsider the very nature of space, time, and matter. As we continue to explore the cosmos, black holes remain one of the most enigmatic and awe-inspiring objects, with the potential to unlock new and unimaginable insights about the universe's most fundamental processes. The search for answers, it seems, is just beginning. Gravitational waves represent one of the most intriguing phenomena in modern astrophysics, offering an entirely new way of exploring the universe. These ripples in the very fabric of space-time were first detected in 2015, marking a groundbreaking achievement in our understanding of the cosmos. Generated when two black holes collide and merge, gravitational waves provide a rare glimpse into these cataclysmic events. The detection of these waves confirmed that black holes do not merely exist as silent, invisible giants. They interact with one another in dramatic and energetic ways, merging to form even larger black holes. This discovery opened a new window into the universe, revealing the dynamic behavior of black holes, their interactions, and the potential for larger cosmic structures to form from these intense collisions. The advent of gravitational wave detection, alongside the study of X-rays and the careful observation of star orbits, has given scientists a multifaceted view of black holes. Though we cannot directly observe black holes since light cannot escape from them, the indirect evidence is incredibly revealing. Observing the way stars behave in their proximity, detecting high-energy X-ray emissions from their accretion disks, and now detecting gravitational waves has created a compelling picture of these cosmic entities. Together, these observations paint black holes as far more than theoretical objects. They are some of the most studied phenomena in modern astrophysics. Their very existence challenges our understanding of the universe, inspiring scientists to continue probing deeper into the mysteries of space and the laws that govern it. One of the most profound challenges to our perception of black holes came in the 1970s from the brilliant mind of physicist Stephen Hawking. His revolutionary theory, known as Hawking radiation, introduced a strikingly new perspective on black holes. Traditionally, black holes had been considered cosmic vacuum cleaners, mysterious objects that devour everything in their vicinity, including light, making them effectively invisible. However, Hawking's theory proposed that black holes are not entirely black after all. Instead, due to quantum mechanical effects near their event horizons, they may emit radiation, a phenomenon now known as Hawking radiation. This revelation suggested a dynamic interplay between black holes and the broader universe, one that fundamentally altered our view of them. As black holes emit Hawking radiation, they gradually lose mass and energy. Over time, this process could lead to their eventual evaporation, a dramatic conclusion to what was once thought to be an eternal existence. The idea that black holes might have a finite lifespan challenges long-standing beliefs and suggests a universe where even the most massive and powerful objects are not immune to the forces of time. The emission of Hawking radiation has far-reaching implications. As black holes lose mass and shrink, they paradoxically become hotter, raising questions about the nature of these entities and their place in the universe. But perhaps even more intriguing is the issue of information, specifically the information that is thought to be lost when matter falls into a black hole. What happens to the information regarding the particles and objects that a black hole consumes? This question has sparked intense debate among physicists, with some proposing the holographic principle, which suggests that all the information within a three-dimensional space could be encoded on its boundary. The resolution of this information paradox is vital for reconciling quantum mechanics with general relativity and understanding the fundamental workings of the universe. Hawking's insights into black holes not only changed the way we think about these cosmic entities, but also bridged the gap between the strange, counterintuitive world of quantum mechanics and the vast, sweeping scale of cosmology. It has pushed the boundaries of our understanding, challenging us to rethink what black holes are and how they fit into the broader fabric of the universe. At the very heart of many galaxies lies a particularly mysterious and powerful class of black holes, supermassive black holes. These giants, often located at the centers of galaxies, including our own Milky Way, are some of the most enigmatic structures in the cosmos. Supermassive black holes likely originate from smaller black holes, which are the remnants of massive stars that have collapsed. Over time, these smaller black holes may merge with others or gather vast amounts of gas and dust from their surroundings through a process called accretion. As this material spirals in toward the black hole, it heats up, emitting intense radiation and allowing the black hole to grow larger. The formation of supermassive black holes is no random process. Rather, it plays a crucial role in shaping the structure and evolution of galaxies. As these black holes grow, they exert immense gravitational forces on nearby stars and gas clouds. This gravitational influence can help organize the material in a galaxy, driving the formation of new stars and guiding the overall structure of the galaxy itself. In this way, supermassive black holes are not only central to the dynamics of their galaxies, but may also serve as key players in the formation of the very galaxies in which they reside. These supermassive black holes, with their massive gravitational pull and complex interactions with their surroundings, remain one of the most captivating and mysterious subjects of study in modern astronomy. Through the combination of advanced observational techniques, including gravitational wave detection, X-ray astronomy, and the study of star orbits, we continue to uncover new facets of their existence and behavior. Their study has the potential to revolutionize our understanding of the universe on the grandest scales, deepening our knowledge of the forces that shape galaxies, stars, and the cosmos itself. Supermassive black holes are not just fascinating cosmic anomalies, they are integral to shaping the very structure of galaxies. Through their immense power, these enigmatic objects regulate star formation in galaxies, primarily through their powerful jets and winds. These colossal outflows sweep away gas and dust from a galaxy's inner regions, limiting the amount of material available for new star formation. This dynamic relationship between black holes and star creation highlights the profound influence these celestial giants exert on their environments. It's as if these black holes serve as gatekeepers, dictating how much new life can arise within the vast expanses of their galaxies. But the relationship between supermassive black holes and galaxies doesn't stop there. There is a captivating connection between the size of a black hole and the characteristics of the galaxy in which it resides. Research has revealed that the mass of a black hole is intricately tied to the mass of the galaxy's bulge. Specifically, the more massive the black hole, the more massive the surrounding galaxy's central bulge. This phenomenon points to a remarkable coevolution, suggesting that black holes and their galaxies grow in tandem. As a black hole evolves, it imprints its influence on the galaxy, shaping not only its physical structure but also its dynamic behavior. The implications of supermassive black holes stretch beyond individual galaxies, touching on the broader evolution of the universe itself. These cosmic behemoths are believed to have played pivotal roles in the early universe, possibly helping to seed the formation of the first galaxies. By studying supermassive black holes, astronomers gain a unique window into the grander cosmic narrative, revealing just how interconnected the universe truly is. It is a vast dance of dark matter, gravity, and the luminous stars we see, each force pulling and pushing the others in an intricate cosmic ballet. Moving to another intriguing concept, primordial black holes are objects theorized to have formed during the earliest moments of the universe, shortly after the Big Bang. These early black holes have a vastly different origin compared to the black holes we study today, which typically form from the collapse of massive stars. Instead, primordial black holes could have a wide range of sizes, from minuscule objects with masses lower than that of asteroids to gargantuan entities that rival or exceed the mass of large stars. Despite the excitement surrounding their potential, primordial black holes remain shrouded in mystery, with many questions still unanswered. A central challenge in studying these primordial objects is their mass distribution. How many primordial black holes exist, and what is their range of masses? Some theories propose that they could form a diverse population, spanning from microscopic black holes to those several times the mass of our Sun. However, without conclusive evidence, the true nature of these objects remains elusive. Understanding their mass distribution is key because it could help explain some of the universe's most profound mysteries, such as the origins of gravitational waves and the behavior of dark matter. Dark matter itself is a critical element in the primordial black hole discussion. While we know that dark matter makes up a significant portion of the universe's mass, its exact nature remains one of cosmology's biggest unanswered questions. Could primordial black holes be a component of this enigmatic substance? This possibility has fueled considerable debate among researchers, but the connection remains speculative. If primordial black holes are indeed linked to dark matter, it raises new questions about how these objects might interact with other forms of matter and energy in the cosmos. The detection of primordial black holes presents a substantial challenge to astronomers. While we've observed countless black holes through various methods, the primordial variety may leave behind subtle signals that we have yet to identify. One potential avenue for discovery involves gravitational lensing, the bending of light caused by massive objects. Additionally, the cosmic microwave background radiation, CMB, could provide clues, as could the elusive Hawking radiation, a theoretical emission predicted by physicist Stephen Hawking. Until we can capture definitive evidence, primordial black holes remain one of the most captivating mysteries in cosmology, continuing to fuel the imaginations of scientists and stargazers alike. The moment before the Big Bang is a question that has puzzled cosmologists for decades. What existed before this monumental event? While many theories attempt to address this enigmatic question, each grapples with the limitations of our understanding of time and space. One popular theory suggests that the Big Bang wasn't just the birth of the universe, but the creation of time and space itself. If this is true, then asking what happened before the Big Bang may be fundamentally nonsensical, because time, as we understand it, didn't exist. In this view, the Big Bang was not only the birth of our universe, but also the dawn of time itself. Another theory posits the idea of cosmic inflation. According to this hypothesis, the universe underwent a brief, yet incredibly rapid expansion shortly after the Big Bang. Some researchers speculate that this inflationary phase might have been preceded by another phase, possibly a different universe entirely. This could suggest a cyclical process of big bangs and collapses, where our universe is just one bubble in an ever-expanding foam of universes, an idea known as the multiverse theory. Lastly, the concept of quantum fluctuations presents another intriguing possibility. At the quantum level, tiny, random fluctuations in energy could have caused the creation of a miniature universe, which then expanded rapidly to become our universe. This view imagines the Big Bang as the result of a chaotic energy fluctuation, setting the stage for the creation of all matter and energy in the cosmos. Each of these theories opens up a new realm of possibilities, underscoring the thrilling uncertainty at the heart of cosmology. Our origins remain as mysterious as they are awe-inspiring, with new discoveries always on the horizon. The nature of the universe and the events leading up to its birth remain one of the most profound and exciting areas of scientific inquiry. To better understand the conditions of the early universe, scientists employ a combination of cutting-edge methods, including theoretical models, astronomical observations, and experimental physics. One of the most important tools in this pursuit is the study of the cosmic microwave background radiation, CMB. This faint afterglow, a remnant from when the universe was a dense, hot soup of particles, was released around 380,000 years after the Big Bang. By analyzing minute temperature fluctuations in the CMB, scientists can infer valuable information about the state of the universe at that time. In addition to observations of the CMB, researchers also use particle accelerators, such as the Large Hadron Collider, to recreate conditions similar to those that existed just after the Big Bang. By accelerating protons to near light speeds and smashing them together, physicists can observe fundamental particles and forces that were present in the early universe. These experimental results offer critical insights into the building blocks of matter and the fundamental forces that govern the universe, providing a deeper understanding of the cosmos and our place within it. Additionally, scientists have turned to advanced computer simulations rooted in the laws of physics to model the evolution of the early universe. These simulations, sophisticated in their design, take into account key physical processes such as cosmic expansion, cooling, and the formation of complex structures like galaxies. By running these simulations and comparing their outcomes with real-world astronomical observations, researchers can refine and adjust their understanding of the processes that shaped the universe into its current form. This powerful combination of theory and observation allows for continuous refinement of cosmological models, bringing us closer to understanding the intricacies of the cosmos and its vast evolutionary history. One of the most crucial sources of information about the universe's past is the light emitted by distant galaxies. This light, which has traveled billions of years to reach us, serves as a time machine of sorts, offering astronomers a glimpse into the distant past. By studying this light, scientists can learn not only how galaxies formed, but also how they evolved over time. The journey of this ancient light provides invaluable data on the conditions that existed in the universe long before Earth even came into being. By piecing together these various lines of evidence, from the cosmic microwave background, CMB, radiation, to particle collisions and observations of far-off galaxies, researchers are slowly but surely uncovering the mysteries of the universe's earliest moments. This ongoing quest transforms theoretical concepts into a more vivid and tangible understanding of our cosmic origins, offering us an ever-deepening comprehension of how everything began. The cosmic microwave background radiation, often abbreviated as CMB, serves as one of the most fascinating relics from the universe's earliest days. This faint glow, which bathes the entire cosmos, is believed to be the remnant radiation from the period just after the Big Bang, occurring approximately 380,000 years following the monumental event. During this time, the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms, which allowed light to travel freely for the very first time. This moment, often referred to as the decoupling era, marks a significant turning point in the universe's evolution, as it allowed light to escape, providing the first observable imprint of the universe in its nascent stages. The discovery of the CMB in the 1960s was nothing short of groundbreaking. It provided the first solid evidence supporting the Big Bang theory, radically changing our understanding of the universe's origin. When scientists began to analyze this background radiation, they found that it is strikingly uniform across the entire sky. However, this uniformity is not perfect. It contains tiny fluctuations that represent minute variations in density and temperature. These fluctuations are far from random. They are the seeds that eventually gave rise to the formation of galaxies and the large-scale structure we observe today. Thus, the CMB not only reveals what the universe looked like shortly after its birth, but it also offers crucial insights into the mechanisms that led to the intricate cosmic structures that we now see. The precise measurements of the CMB have also allowed cosmologists to determine key parameters of the universe. These observations have revealed that the universe is approximately 13.8 billion years old, composed primarily of dark energy and dark matter, with ordinary matter making up only a small fraction. These groundbreaking findings have reshaped our understanding of the cosmos, raising new questions about the nature of dark energy, which appears to be responsible for the accelerated expansion of the universe. As a result, the CMB serves not just as a snapshot of the universe's early days, but also as a crucial tool for investigating the present and future of the cosmos. And in many ways, the cosmic microwave background radiation can be considered a time capsule, a snapshot of the universe at a moment when it was young and still in the throes of its formative stages. The study of the CMB provides vital clues about the origins and evolution of the universe, and as technology continues to advance, researchers are able to peel back additional layers of understanding, revealing new details about the universe's past. With each new discovery, scientists get closer to unlocking the enduring mysteries of the cosmos, offering us a deeper sense of our place within this vast and ever-evolving universe. The Big Bang Theory has long been the dominant explanation for the origin and evolution of the universe. However, in recent years, scientists have started to explore alternative models that offer different perspectives on the universe's beginnings. One such alternative is the steady-state theory, which proposes that while the universe is indeed expanding, it maintains a constant average density over time. According to this theory, as galaxies move further apart, new matter is continually created to fill the voids between them, ensuring that the overall density of the universe remains unchanged. In this model, the universe is seen as eternal and unchanging, a stark contrast to the dynamic and evolving universe described by the Big Bang Theory. While the steady-state theory does not have the widespread acceptance that the Big Bang Theory enjoys, it nonetheless represents an important part of the ongoing debate over the universe's origins. As scientists continue to explore and refine these competing theories, the mysteries of the cosmos become ever more intriguing, and our understanding of the universe's beginnings continues to evolve. Each new theory or discovery builds upon the knowledge of those that came before it, advancing our quest to understand the vast, complex, and awe-inspiring nature of the universe.